The continents we know today, North America, Africa, Asia, were once joined together in a single massive landmass. This ancient supercontinent was called Pangea. It wasn't just a theory drawn from maps or fossils. Geologists have uncovered powerful evidence in the rocks, mountains, and coastlines that line up across oceans. But the full story of Pangea is still unfolding. New research using satellite imaging, seismic data, and deep Earth scanning is revealing strange patterns buried far beneath the surface. They're finding pieces of lost continents, signs of ancient collisions, and movements that shaped everything we see today. This isn't just about land breaking apart. It's about the hidden forces deep inside the planet that continue to shift and crack the surface. What caused Pangea to form? And why did it break apart? What secrets are buried in the crust that once held it all together? This documentary explores the formation, life, and breakup of Earth's last great supercontinent. Imagine a world where all the land masses we know today were huddled together, a single, immense, and awe-inspiring supercontinent dominating the Earth's surface. This is the story of Pangea, a name that conjures images of a primordial Earth, a colossal landmass that played an utterly pivotal role in shaping the planet we inhabit. To truly grasp the sheer scale and significance of Pangea, we must first understand what a supercontinent actually is. Think of it not just as a large landmass, but as a monumental accumulation of most, if not all, of the continental crust on our planet, gathered together in one colossal expanse. Pangea wasn't merely a big piece of land. It was a global phenomenon, a geological epoch defined by its existence. The sheer size of Pangea is almost beyond human comprehension. Picture the land area of all our modern continents: North America, South America, Europe, Asia, Africa, Australia, and Antarctica, all connected, forming an uninterrupted expanse. This vast landmass stretched from pole to pole, creating a unique and dramatically different world compared to the one we experience today. The configuration of Pangea, with its roughly C-shape or horseshoe outline, significantly influenced everything from global climate patterns and ocean currents to the evolution and distribution of life. Its existence meant that, for a considerable period, terrestrial animals could theoretically walk from what is now Antarctica all the way up to the northern reaches of Canada without ever crossing an ocean. This was a world of unprecedented connectivity for land-dwelling creatures, fostering interactions and migrations on a truly grand scale. The story of Pangea unfolds across a vast sweep of Earth's history, primarily spanning the late Paleozoic era and extending into the early Mesozoic era. Its grand assembly began in earnest around 335 million years ago, during the Carboniferous period. This wasn't a sudden coming together, but rather a slow, inexorable process, a monumental collision of precursor continents such as Gondwana, itself a massive southern landmass comprising South America, Africa, Antarctica, Australia, and India, and Laurasia, which would later split into North America, Europe, and most of Asia. Over millions of years, these massive continental blocks, propelled by the unseen forces deep within the Earth, gradually converged and fused, stitching together the seams of ancient oceans until they formed the cohesive supercontinent we call Pangea. The period of Pangea's most complete coherence, its peak existence, lasted throughout the Permian period and into the early part of the Triassic period, roughly from about 299 million years ago to around 200 million years ago. This was its golden age, a time when the world was largely defined by this single, dominant landmass. However, even supercontinents are not eternal. The slow, powerful forces that brought Pangea together eventually began to pull it apart. The breakup of Pangea commenced during the Middle Jurassic period, around 175 million years ago. This rifting process, which started with initial cracks and fissures, gradually widened into vast ocean basins, eventually leading to the configuration of continents we recognize today. It was a testament to the dynamic and ever-changing nature of our planet. So, why does Pangaea, a landmass that existed hundreds of millions of years ago, matter so profoundly in Earth's history? Its significance is multifaceted, leaving an indelible mark on geology, climate, and the very trajectory of life itself. From a geological perspective, the formation of Pangaea was an event of monumental mountain building. The colossal collisions between the converging continental plates created some of the world's most ancient and majestic mountain ranges. For example, the Appalachian Mountains in eastern North America, the Caledonian Mountains in Europe, and the Ural Mountains in Russia are all direct legacies of the Pangean assembly. These towering ranges bear witness to the immense forces that reshaped the Earth's crust. Conversely, the breakup of Pangea was equally transformative. As the supercontinent began to fragment, new oceanic crust was generated along spreading ridges, leading to the birth of vast ocean basins, most notably the Atlantic Ocean. The gradual widening of these oceans continues to this day, pushing the continents further apart and shaping the maritime geography of our planet. The impact of Pangaea on global climate was equally profound. Its sheer size and unique configuration led to a supercontinental climate characterized by extreme temperatures and pronounced aridity over much of its interior. Far from the moderating influence of oceans, the vast landmass experienced scorching hot summers and frigid cold winters, leading to conditions similar to modern-day deserts. The absence of numerous smaller continents meant that global ocean currents were organized differently. There were fewer barriers to warm water circulation around the equator, potentially leading to hotter global temperatures overall. This super-ocean, Panthalassa, which surrounded Pangaea, also contributed to unique atmospheric circulation patterns, including powerful monsoons that would have drenched coastal regions for part of the year, while leaving the interior parched for the rest. Understanding these ancient climate patterns provides crucial insights into the complex interactions between land masses, oceans, and the atmosphere. Perhaps one of the most fascinating aspects of Pangaea's legacy lies in its influence on life. The existence of a single landmass allowed for an unprecedented scale of terrestrial migration. Animals could roam freely across what are now vastly separated continents, leading to widespread genetic mixing and the development of broadly distributed faunal communities. The fossil record is replete with evidence of this. For instance, the discovery of identical reptile and amphibian fossils, such as the small freshwater reptile Mesosaurus, or the land-dwelling therapsid Lystrosaurus, on continents now thousands of kilometers apart, like South America and Africa, or Africa and Antarctica, provides compelling proof of this ancient connectivity. This facilitated the evolution and diversification of many groups, including the early dinosaurs, which rose to prominence during the Triassic period, thriving across a unified Pangean landscape. Early mammals and various forms of reptiles also spread widely. Similarly, the flora of Pangaea also reflected this unity. The widespread distribution of certain ancient plant species, like the fern Glossopteris, whose fossils are found across South America, Africa, India, Australia, and Antarctica, further underscores the existence of a connected landmass. The presence of these plants in diverse modern climates, from tropical to polar, suggests that the continents must have been joined and then moved to their current positions. The immense forests and plant life of Pangaea played a vital role in global ecosystems and contributed significantly to the carbon cycle of the time. The formation and breakup of Pangaea are also inextricably linked to some of the most dramatic events in Earth's history, including mass extinctions. The Permian Triassic extinction event, often dubbed the Great Dying, which occurred around 252 million years ago, wiped out approximately 96% of marine species and 70% of terrestrial vertebrate species. While the exact causes are debated, the extreme climatic conditions associated with Pangaea's existence and the massive volcanic eruptions, like the Siberian traps that may have been triggered by the supercontinent's formation and subsequent rifting are often cited as significant contributing factors. The breakup of Pangea, in turn, reshaped environments, creating new coastlines, mountain ranges, and climatic zones, which then drove further evolutionary diversification and adaptation in the newly separated landmasses. Finally, Pangea matters because it is the direct ancestor of our modern geography. The shape of our continents, the distribution of natural resources, and even the patterns of ocean currents today are all direct consequences of Pangea's fragmentation and the subsequent movement of its pieces. Understanding Pangea is not merely an exercise in historical geology. It is fundamental to comprehending why the world looks the way it does today. Moreover, Pangea serves as a powerful reminder that our planet is dynamic, a place of constant, slow but immense change. Pangea was not the first supercontinent in Earth's history. Others, like Rodinia and Columbia, preceded it, and it will almost certainly not be the last. Geologists believe that the supercontinent cycle, the rhythmic assembly and breakup of continents, is an inherent part of Earth's long-term geological processes. By studying Pangea, we gain a deeper understanding of this grand cycle, allowing us to peer into both the deep past and potentially the distant future of our ever-evolving planet. Its legend is not just a tale of what was, but a key to understanding what is and what might yet be. For much of human history, the continents seemed like immovable, eternal fixtures on the Earth's surface. The idea that entire landmasses could slowly drift across the globe, changing their positions over vast stretches of time, was a concept so radical it was met with widespread skepticism and even outright ridicule for many decades. Yet, this once unthinkable notion, now known as plate tectonics, stands as the unifying theory of geology, explaining a myriad of Earth's most dramatic phenomena, from earthquakes and volcanoes to the formation of towering mountain ranges and the distribution of ancient life. At its heart, plate tectonics describes how the Earth's outer shell, known as the lithosphere, isn't a single, solid sphere, but rather a patchwork of enormous, rigid plates that are constantly in motion, albeit at speeds that are imperceptible to human observation, typically a few centimeters per year, about as fast as your fingernails grow. These tectonic plates, some carrying continents and others consisting solely of oceanic crust, interact at their boundaries in three fundamental ways. At divergent boundaries, plates pull apart, allowing molten rock from the Earth's mantle to rise and create new crust, exemplified by the majestic mid-ocean ridges. Convergent boundaries are where plates collide, leading to spectacular events, such as the formation of mountain ranges when two continental plates meet, or the subduction of an oceanic plate beneath another plate, creating deep ocean trenches, volcanic arcs, and intense seismic activity. Lastly, transform boundaries occur where plates slide past each other horizontally, often resulting in significant earthquakes as stress builds up and is suddenly released along fault lines, like California's San Andreas Fault. Understanding these interactions is key to understanding the dynamic nature of our planet. The driving force behind this monumental movement is believed to be convection currents within the Earth's incredibly hot, viscous mantle. Picture a pot of boiling water where heat rises, cools, and sinks, creating a circular motion. Similarly, heat from the Earth's core causes hotter, less dense material in the mantle to rise, while cooler, denser material sinks, slowly dragging the overlying tectonic plates along with it. The journey to accepting this revolutionary understanding of our planet was a long and arduous one, spearheaded by a remarkable individual named Alfred Wegener. Born in Germany in 1880, Wegener was not a geologist by profession. He was a meteorologist and a polar researcher, a scientist with a keen eye for observation and a mind unburdened by conventional geological wisdom. It was around 1912 that Wegener first publicly proposed his groundbreaking hypothesis of continental drift. He was captivated by the striking similarity in the coastlines of continents on opposite sides of the Atlantic Ocean, particularly the near-perfect fit between South America and Africa, as if they were pieces of a giant jigsaw puzzle that had once been joined. Wegener wasn't the first to notice this jigsaw-like fit, but he was the first to systematically gather a comprehensive body of evidence to support the idea that continents had indeed moved. His evidence was compelling and multidisciplinary. Beyond the obvious fit of the continents, he meticulously documented fossil evidence that was perplexing if continents had always been in their current positions. For instance, fossils of the small, freshwater reptile, Mesosaurus, were found only in South America and Africa. This creature, unable to cross vast oceans, suggested that these two landmasses must have been connected when it lived. Similarly, the land-dwelling reptile Lystrosaurus, a relatively slow-moving animal, and Cynognathus, another land reptile, were found on continents separated by enormous oceanic stretches, again indicating a former land bridge, or more accurately, a unified landmass. Perhaps most famously, the fossilized leaves of the ancient fern Glossopteris were discovered across South America, Africa, India, Australia, and Antarctica. This plant's distribution was utterly baffling if these continents were always separated. Furthermore, Wegener looked at rock type and structural similarities. He noted that ancient mountain ranges, such as the Appalachian Mountains in eastern North America, seemed to align perfectly with the Caledonian Mountains in Europe and the Atlas Mountains in northwestern Africa when the continents were notionally reassembled. These mountain belts exhibited similar rock types, ages, and geological structures, suggesting they were once part of a single, continuous mountain range formed during the same ancient collision. He also found remarkable similarities in the sequences of rock layers found on widely separated continents. Finally, Wegener presented compelling paleoclimate evidence. He found evidence of extensive glaciation in the form of glacial striations and tillites, deposits left by glaciers, in tropical regions like parts of India, Australia, and Africa. This seemed nonsensical unless these land masses had once been located closer to the poles. Conversely, he found ancient coal deposits, which form in warm, swampy environments in regions that are now polar, like Antarctica. This suggested that Antarctica must have once been closer to the equator. This array of evidence, drawing from geology, paleontology, and climatology, painted a powerful picture of continents that had indeed moved. Despite the strength of his evidence, Wegener's theory faced tremendous resistance and skepticism from the scientific community of his time. The primary reason for this rejection was a critical missing piece. Wegener lacked a plausible mechanism for how continents could possibly move. He proposed that continents plowed through the oceanic crust, or that centrifugal force from the Earth's rotation and tidal forces were responsible. These proposed mechanisms were demonstrably insufficient to move entire continents, and were easily disproven by physicists. Without a credible driving force, many geologists simply could not accept the idea. The prevailing geological paradigm at the time was that the Earth was a largely static body, with mountains forming through vertical movements of the crust, not horizontal continental collisions. Furthermore, Wegener was a meteorologist, not a trained geologist, which might have contributed to some resistance from the established geological community, who viewed him as an outsider encroaching on their field. It was a classic example of a brilliant hypothesis that was ahead of its time, awaiting the discovery of the underlying physical processes. The mid-20th century, particularly the 1950s and 1960s, brought about a revolution in earth sciences that finally provided the missing pieces and vindicated Wegener's vision. The crucial breakthrough came with the understanding of seafloor spreading, pioneering work by American geophysicist Harry Hess and Canadian geologist Robert Dietz proposed that new oceanic crust was continuously being generated at mid-ocean ridges, which are vast underwater mountain ranges that snake around the globe. As new molten material rises from the mantle and solidifies, it pushes the older crust away from the ridge in a conveyor belt-like fashion. The The most compelling evidence for seafloor spreading came from the study of paleomagnetism. Scientists discovered that as new oceanic crust forms at mid-ocean ridges, the iron-rich minerals within the cooling rock aligned themselves with the Earth's magnetic field, effectively recording its direction and polarity at that moment in time. Critically, the Earth's magnetic field periodically reverses its polarity, meaning that the North Pole becomes the South Pole and vice versa. These magnetic reversals, occurring every few 100,000 years to several million years, are recorded as parallel stripes of normally and reversely magnetized rock on the ocean floor, symmetrically distributed on either side of the mid-ocean ridges. This pattern of magnetic striping acts like a giant tape recorder of the seafloor spreading process, providing undeniable proof that new crust is being created and pushed outward. Furthermore, scientific drilling expeditions into the ocean floor confirmed that the oceanic crust became progressively older with increasing distance from the mid-ocean ridges, just as the seafloor spreading hypothesis predicted. In addition to seafloor spreading, modern technology has provided increasingly precise and irrefutable evidence for plate movement. The Global Positioning System, or GPS, which relies on a network of satellites orbiting the Earth, can now directly measure the movement of tectonic plates down to a few millimeters per year. By placing GPS receivers at various locations on different continents, scientists can track their precise positions over time and observe their gradual but continuous drift. These real-time measurements provide the ultimate confirmation that continents are indeed moving, and at rates entirely consistent with those predicted by geological models. This direct observation truly silenced any remaining doubters. The study of rock formations has also advanced significantly since Wegener's time, providing even stronger support for plate tectonics. Scientists can now use more sophisticated dating techniques to precisely correlate rock sequences across continents, further confirming the geological linkages Wegener observed. The patterns of deformation, including immense folds and faults found in mountain ranges that align across continents, are now understood as the direct result of past continental collisions. Furthermore, the distribution of active volcanoes and the epicenters of earthquakes around the globe are not random. They cluster along the very boundaries of the tectonic plates, providing dramatic real-time evidence of the interactions between these moving segments of the Earth's lithosphere. Deep-sea drilling programs have allowed geologists to sample oceanic crust and sediments, providing invaluable data about the age, composition, and formation processes of the ocean basins, all consistent with plate tectonic theory. Techniques like seismic tomography, which uses earthquake waves to create three-dimensional images of the Earth's interior, have revealed the presence of mantle plumes, upwellings of hot rock, and subducting slabs, downward-moving plates, lending further support to the concept of mantle convection as the driving force behind plate motion. The journey from Wegener's initially ridiculed idea of continental drift to the universally accepted theory of plate tectonics is one of the greatest success stories in science. It demonstrates the power of observation, the importance of a multidisciplinary approach, and the eventual triumph of evidence over skepticism. Today, plate tectonics is not just a theory. It is the fundamental framework through which we understand the dynamic, ever-changing nature of our planet, providing insights into its past, present, and future. It's the mechanism that brought Pangea together and tore it apart, shaping the world we inhabit and the very distribution of life on Earth. When we talk about Earth's deep past, and especially about its grand continental arrangements, Pangea often steals the spotlight. It was, after all, the most recent and arguably the most famous of the supercontinents, the one whose breakup laid the groundwork for the world map we recognize today. But to truly understand Pangea, and to appreciate the incredibly dynamic nature of our planet, we need to look much further back in time, to the ages before its majestic assembly. Pangea wasn't a unique occurrence. It was merely the latest in a long, recurring series of colossal landmasses that have profoundly shaped Earth's geology, climate, and the very course of life itself. The story of supercontinents is one of cyclical formation and fragmentation, a grand tectonic dance orchestrated by the slow, powerful churn of Earth's mantle. This rhythmic process, known as the supercontinent cycle, has repeated itself over billions of years, leaving indelible marks on the crust and providing invaluable clues about our planet's inner workings. By studying the predecessors to Pangea, supercontinents like Kenorland, Columbia, and Rodinia, scientists have pieced together an extraordinary narrative of our planet's evolution, each ancient landmass offering a unique lesson about the Earth's dynamic processes. Let's cast our minds back, way back, to the very dawn of complex continental crust, to a time so ancient that life was still in its earliest, simplest forms. Our journey begins in the Neo-Archean era, a period roughly 2.7 billion to 2.5 billion years ago, with a supercontinent that scientists have named Kenorland. This incredibly ancient landmass is perhaps the earliest proposed supercontinent for which there is substantial geological evidence. Imagine a world vastly different from our own. The atmosphere was likely very different, perhaps less oxygenated, and the sun might have been dimmer. Yet beneath the surface, the engines of plate tectonics were already at work. Kenorland wasn't formed from the collision of modern-day continents as we know them, but rather from the aggregation of numerous smaller protocontinents and ancient cratons, the stable, incredibly old cores of today's continents. Some of the key building blocks of Kenorland included the Baltic Shield, which forms the core of Scandinavia and Eastern Europe, the Superior Craton of North America, and the Yilgarn Craton of Western Australia. Geologists piece together the existence of Kenorland not by finding a neat, unbroken landmass, but by analyzing patterns in ancient rocks. Paleomagnetic data, which tells us about the orientation of Earth's magnetic field encoded in rocks at the time they formed, suggests that these now separated cratons were once connected in a specific configuration. Further evidence comes from geological similarities, such as matching rock sequences, mineral deposits, and the ages of ancient mountain belts that would have formed during its assembly. The formation of Kenorland was a monumental event, signifying the stabilization of large volumes of continental crust. Before this, Earth's crust was likely more fragmented and perhaps underwent a faster, more vigorous form of tectonics due to a hotter mantle. Kenorland's existence suggests a transition towards more modern-style plate tectonics, where continental masses could grow larger and persist for longer periods. However, like all supercontinents, Kenorland was not destined to last. Its breakup, which began around 2.5 billion years ago, was likely driven by the intense heat within Earth's mantle. Scientists propose that large mantle plumes, rising columns of hot rock from the deep mantle, may have impinged upon the underside of the supercontinent, causing it to dome upwards, stretch, and eventually rift apart. This rifting would have been accompanied by widespread volcanic activity, spewing molten rock onto the surface and creating vast igneous provinces. The fragmentation of Kenorland led to the formation of new ocean basins and the dispersal of its constituent cratons across the globe. What Kenorland taught us is profound. It showed us that the supercontinent cycle is an ancient phenomenon, stretching back billions of years into Earth's history. It provided insights into the very early stages of continental crust formation and stabilization, suggesting that even in the Archean, continental masses were not static, but were actively participating in a grand tectonic dance. Its breakup also provided some of the earliest evidence for the role of large igneous provinces, LIPs, in fracturing continents, a mechanism that continues to be observed in later supercontinent breakups. Moving forward in geological time, past the Kenorlandian fragmentation, we arrive at the Paleo-Proterozoic era, roughly 1.8 billion to 1.5 billion years ago, which saw the assembly of another colossal landmass known as Columbia, sometimes also referred to as Nuna. Columbia was a significantly larger and more complex supercontinent than Kenorland, reflecting the continued growth and maturation of Earth's continental crust. Its assembly involved the collision of numerous Archean cratons that had dispersed after Kenorland's breakup, along with the accretion of newly formed Paleo-Proterozoic crust. Imagine the sheer scale of these collisions. Land masses the size of present-day continents, slowly but inexorably grinding against one another, crumpling their margins into vast mountain ranges that would have dwarfed anything we see today. Key components of Columbia included what would become Laurentia, the ancient core of North America, Baltica, Scandinavia and Eastern Europe, Siberia, North China, West Africa, and parts of Australia. The evidence for Columbia's existence is even stronger than for Kenorland. Geologists have identified extensive orogenic belts, the remnants of ancient mountain ranges that formed during its assembly. For example, the Trans-Hudson Orogen in North America, a vast belt of deformed rocks stretching across central Canada and the northern United States, is a prime example of a mountain-building event that contributed to Columbia's formation. Beyond these collisional features, there is also widespread anorogenic magmatism, which means igneous activity that occurs without obvious mountain building, often associated with the thermal relaxation and stretching of the crust after a period of continental assembly. The breakup of Columbia, which began around 1.5 billion years ago, was also a protracted process, involving rifting events that gradually pulled the supercontinent apart and led to the formation of new ocean basins. What Columbia taught us was critical for understanding the evolution of plate tectonics. It demonstrated that the scale of continental collisions was increasing and that plate tectonic processes were becoming more robust and similar to those operating today. Its assembly and breakup had profound implications for the early Earth's environment and the evolution of life. The Great Oxidation Event, which saw a significant rise in atmospheric oxygen, largely preceded Columbia's assembly, but its breakup may have influenced nutrient cycling in the oceans, potentially playing a role in the diversification of early eukaryotic life. The long period of relative tectonic stability associated with Columbia, often referred to as the boring billion by geologists due to the apparent lack of dramatic evolutionary innovation in the fossil record, offers a fascinating insight into how supercontinent stability can influence biological evolution. Our next stop on this journey through Earth's ancient supercontinents brings us to the Neo-Proterozoic era, roughly 1.1 billion to 750 million years ago, and the formation of Rodinia. If Pangea is the most famous supercontinent, then Rodinia is perhaps the second most, largely because its breakup is intimately linked with some of the most dramatic events in Earth's history, including the snowball Earth glaciations and the subsequent explosion of complex life. Rodinia means homeland in Russian, and it was a truly enormous landmass, likely centered around what would become Laurentia, North America. Its formation was largely driven by the Grenville orogeny, a global mountain-building event that occurred between 1.3 billion and 1 billion years ago. This was a period of intense continental collision, as various land masses, including parts of present-day South America, Africa, Australia, India, and Antarctica, converged around Laurentia. The Grenville mountain belts, now eroded down to their ancient roots, can still be found on multiple continents, providing compelling evidence of their once-connected nature. Rodinia's existence is supported by extensive geological and paleomagnetic data. The distribution of similar rock types and geological histories across now separated continents strongly suggests their past continuity. For instance, the Grenville Age rocks in eastern North America find their counterparts in the British Isles, Scandinavia, and even in Antarctica, indicating a shared tectonic past within Rodinia. The breakup of Rodinia, beginning around 750 million years ago and continuing for a couple of 100 million years, was a catastrophic process with global consequences. Like its predecessors, its fragmentation is thought to have been driven by mantle plume activity. A superplume, an extraordinarily large rising column of hot mantle rock, may have impinged beneath Rodinia, causing it to dome and rift apart. This rifting led to the opening of new ocean basins, including the precursor to the vast Panthalassic Ocean that would eventually surround Pangea. What Rodinia taught us was nothing short of revolutionary. Its breakup is deeply intertwined with the cryogenian glaciations, the infamous snowball Earth events that saw Earth's surface almost entirely covered in ice. The connection lies in the processes unleashed by the supercontinent's fragmentation. As Rodinia broke apart, vast new continental shelves were exposed to weathering, which drew down enormous amounts of carbon dioxide from the atmosphere, leading to a dramatic cooling of the planet. Furthermore, the volcanic activity associated with rifting could have initially warmed the planet, but the subsequent rifting and continental exposure became a dominant cooling factor. This catastrophic cooling, paradoxically, created conditions that eventually led to a rapid diversification of life. The severe environmental stress likely spurred evolutionary innovation, setting the stage for the rise of the Ediacaran biota, the first large, complex, multicellular organisms, and ultimately the Cambrian explosion, a period of unprecedented biological diversification. Rodinia thus revealed the intricate connection between deep Earth processes, mantle plumes and plate tectonics, and surface events, climate change, and the evolution of complex life. It showed us how the assembly and breakup of supercontinents don't just reshape geology, but also profoundly alter Earth's climate, ocean chemistry, and the trajectory of life itself. These three supercontinents, Kenorland, Columbia, and Rodinia, are not just isolated chapters in Earth's history. They are integral parts of a grand, overarching narrative, the supercontinent cycle. This concept describes the periodic assembly and breakup of continental land masses over geological time, a process driven by the slow but relentless churn of Earth's mantle. While the exact mechanisms are still debated, two main models exist: the introversion model, where the supercontinent forms by the closure of internal oceans, and the extraversion model, where it forms by the closure of external oceans. Regardless of the precise mechanism, the general idea is that continents come together, form a large landmass, heat up from below due to the insulating effect of the thick continental crust, and then eventually rift apart, dispersing their fragments across the globe, only for them to begin a new journey towards collision and reassembly. A typical cycle duration is estimated to be around 300 million to 500 million years, a timescale that seems impossibly vast to human minds, but is a mere blink in geological time. The supercontinent cycle is far more than just a geological curiosity. It is a fundamental driver of Earth's system. Its periodic rhythm controls global climate in profound ways. When continents are assembled into a supercontinent, large interior regions become arid due to their distance from moisture-bearing winds. This also affects global ocean circulation patterns, potentially restricting warm currents and influencing heat distribution. The albedo, or reflectivity, of the Earth's surface also changes depending on the distribution of land masses and ice sheets. Furthermore, the cycle influences the carbon cycle. Supercontinent breakup leads to increased rifting and volcanic activity, releasing carbon dioxide into the atmosphere and potentially causing global warming. Conversely, the increased weathering of newly exposed continental crust during breakup can draw down carbon dioxide, leading to cooling, as seen during the cryogenian. The cycle also drives sea level changes. When continents are dispersed, there is more extensive mid-ocean ridge activity, which displaces ocean water and leads to higher sea levels. When continents are assembled, mid-ocean ridge activity generally slows, leading to lower sea levels. Crucially, the supercontinent cycle has had a profound impact on evolution. The formation and breakup of supercontinents create and destroy habitats, leading to periods of isolation and speciation, or, conversely, widespread competition and even mass extinctions. New continental shelves created during rifting provide vast, shallow marine environments that are ideal for the diversification of marine life, as observed during the Cambrian explosion after Rodinia's breakup. Finally, The supercontinent cycle helps explain the distribution of many valuable mineral deposits. Many ore bodies form during specific phases of the cycle, such as during intense magmatism associated with rifting, or during the crushing pressures of continental collisions. In essence, Kenorland taught us about the infancy of the supercontinent cycle, demonstrating that this rhythmic assembly and breakup of land masses began incredibly early in Earth's history, laying the groundwork for continental crust stabilization and the development of early tectonic processes. Columbia showcased the increasing scale and complexity of continental collisions, hinting at the emergence of more modern-style plate tectonics and its influence on early environmental conditions. Rodinia, perhaps the most illuminating of all, provided a dramatic illustration of how supercontinent breakup could trigger catastrophic climate changes like snowball Earth, yet simultaneously act as a crucible for the evolution of complex life, proving the intricate, often surprising links between deep Earth processes and the trajectory of life on its surface. Each ancient supercontinent, therefore, is not just a name in a textbook. It's a chapter in the grand saga of Earth, offering invaluable lessons that help us understand the forces that shaped our planet and the life that inhabits it, setting the stage for the eventual, magnificent assembly of Pangea. The story of Pangea, the colossal supercontinent that dominated Earth's landmass for hundreds of millions of years, isn't just a tale of geology. It's a vibrant, dynamic narrative woven into the very fabric of life's evolutionary journey. To truly appreciate the grand assembly of Pangea, we must immerse ourselves in the era that immediately preceded and witnessed its slow, inexorable formation, the Paleozoic era. Spanning from roughly 541 million years ago to 252 million years ago, the Paleozoic, often called the Age of Ancient Life, was a time of unprecedented biological innovation, dramatic shifts in climate, and the relentless march of continents across the globe. It was an era where the Earth's land masses were fragmented, but moving with purposeful determination, engaged in a grand, slow-motion dance that would ultimately culminate in the greatest collision in Earth's history. This was a time when life exploded from the oceans onto land, when vast forests covered continents, and when the stage was set for the rise of reptiles, all influenced by the tectonic ballet of two primary continental players, Gondwana and Laurasia. At the beginning of the Paleozoic, Earth was a patchwork of continents, many of them remnants of Rodinia's breakup. While fragmented, two dominant continental masses were already taking shape and would largely dictate the geographical narrative of the era. These were the enormous land masses of Gondwana and Laurasia. It's important to understand that Gondwana was not a new entity formed during the Paleozoic. Rather, it was an ancient, pre-existing supercontinent that had assembled in the Neo-Proterozoic era from the fragments of Rodinia's breakup. By the start of the Paleozoic, Gondwana was already a significant, cohesive landmass, and it remained the largest continental block throughout much of the era. Its constituent parts, which would eventually separate to form many of the continents we know today, included South America, Africa, Antarctica, Australia, India, Madagascar, the Arabian Peninsula, and even bits of Florida and South China. At the dawn of the Paleozoic, roughly 541 million years ago, Gondwana was positioned largely in the southern hemisphere, with a significant portion of its landmass located near the South Pole. Imagine this immense continent, slowly but surely drifting northward over millions of years, a colossal landmass charting a course across the globe. This northward drift had profound consequences for its climate and the life it supported. As Gondwana moved, different parts of it passed through various climatic zones. During certain periods, particularly the Ordovician and the Carboniferous, large portions of Gondwana experienced extensive glaciations, leaving behind telltale signs like glacial striations, scratches on rocks, in areas that are now tropical, such as parts of Africa and India. This evidence is a powerful testament to Gondwana's ancient polar wonder. The vast interior regions of Gondwana, especially as it drifted into warmer latitudes, would have become increasingly arid, creating stark desert landscapes. However, other parts, especially coastal regions and those in more temperate zones, supported thriving ecosystems. The distinctive Gondwana flora, characterized by plants like Glossopteris and its relatives, would eventually spread across this vast landmass, becoming a critical piece of evidence for its former unity. Gondwana's movement wasn't just about land, it also profoundly influenced global ocean currents and climate patterns, affecting the distribution of heat and moisture across the planet, and thus shaping the evolution and distribution of marine and terrestrial life. While Gondwana dominated the southern hemisphere, the northern hemisphere during the early Paleozoic was home to a collection of smaller continents that would eventually come together to form Laurasia. These included Laurentia, comprising most of modern-day North America and Greenland, Baltica, encompassing Scandinavia and Eastern Europe, Siberia, and several smaller land masses like Avalonia, parts of eastern North America, Britain, and Ireland. Unlike Gondwana, which was already a largely assembled entity, Laurasia was a composite continent that began its proper assembly later in the Paleozoic through a series of dramatic collisions among these smaller fragments. These components were drifting independently in the northern hemisphere, undergoing their own intricate dances of separation and convergence, all leading towards a grand eventual union. As these northern landmasses moved and collided, they also experienced diverse climatic zones, from vast shallow seas teeming with marine life to emerging terrestrial environments. The flora and fauna that evolved on these separate continents developed distinct characteristics, setting them apart from the life found on Gondwana, until the eventual supercontinental union would allow for a mingling of these evolutionary pathways. The entire Paleozoic era can be viewed as a colossal, agonizingly slow, but ultimately inevitable dance toward collision. This dance was not a single event, but a series of monumental continental collisions, each one building upon the last, ultimately culminating in the formation of Pangea. These collisions resulted in some of the greatest mountain-building events, or orogenies, in Earth's history, leaving behind geological scars that are still visible today. One of the earliest and most significant of these collisions was the Caledonian orogeny, which occurred primarily during the Silurian and Devonian periods, around 440 million to 390 million years ago. This was the mighty convergence of Laurentia, Baltica, and Avalonia. As these continents ground together, the ancient Iapetus Ocean, which had separated them, slowly closed. The immense forces of this collision crumpled and uplifted vast tracts of crust, forming extensive mountain ranges. The Appalachian Mountains of eastern North America, though significantly eroded, are a legacy of this event, specifically the Appalachian precursors from Avalonia colliding with Laurentia, as are the Scottish Highlands, the Scandinavian mountains, and parts of the mountains in Greenland. This collision effectively formed a new continental mass in the northern hemisphere known as Euramerica or Laurasia. A later phase, specifically within the broader Caledonian, was the Akkadian orogeny, Devonian period, which saw the more direct collision of Avalonia with Laurentia, contributing further to the growing mountain chains and the consolidation of these northern land masses. The final climactic phase of this tectonic dance involved the much larger continents of Gondwana and Laurasia. This grand collision occurred primarily during the Carboniferous and Permian periods, roughly 320 million to 250 million years ago, and involved two major contemporaneous orogenic events, the Alleghanian orogeny and the Variscan-Hercynian orogeny. The Alleghanian orogeny was the monumental collision of Africa, a major part of Gondwana, with eastern North America, part of Laurasia. The sheer scale of the forces involved in this impact was immense, leading to the final, grand uplift of the Appalachian Mountains. At the same time, across the newly forming Pangea, the Variscan or Hercynian orogeny was occurring, representing the collision of parts of Gondwana, specifically Africa and smaller microcontinents, with parts of Europe. This formed extensive mountain belts across Central and Southern Europe, including the precursors to the Alps, Pyrenees, and Urals. These collisions weren't just about creating mountains. They involved massive crustal deformation, widespread volcanic activity, and deep crustal metamorphism, fundamentally reshaping the Earth's surface and interior. The collective result of these protracted collisions was the assembly of Pangea, a singular supercontinent that stretched from pole to pole, surrounded by the vast Panthalassic Ocean. While the continents were slowly converging, life on Earth was undergoing its own incredible transformations. The Paleozoic era began with the Cambrian explosion, around 541 million years ago, a period of rapid diversification where nearly all major animal phyla appeared in the fossil record within a relatively short span of time. This explosion of life was largely confined to the oceans, thriving in the vast, shallow marine environments created by the breakup of Rodinia, which had exposed new continental shelves and provided abundant nutrients. Throughout the Ordovician period, 485 million to 443 million years ago, life continued to diversify in the seas, with the appearance of the first vertebrates, rudimentary fish. Towards the end of the Ordovician, primitive non-vascular plants began to colonize the land, marking a pivotal moment in Earth's history. However, this period ended with a major mass extinction event, possibly linked to the movement of Gondwana over the South Pole, triggering a period of glaciation and associated sea level fall. The Silurian period, 443 million to 419 million years ago, saw the continued evolution of fish, including the appearance of jawed fish. On land, vascular plants became more widespread, and the first terrestrial arthropods, like millipedes and scorpions, began to emerge. The continental movements during this time were influencing ocean currents and creating new environments for marine life. The Devonian period, 419 million to 359 million years ago, often called the Age of Fish, witnessed an extraordinary diversification of fish species. More significantly, it was during this period that the first amphibians ventured onto land, marking the transition from aquatic to terrestrial vertebrate life. Forests began to appear, dominated by early tree-like plants, fundamentally altering the terrestrial landscape. The ongoing continental movements played a crucial role in shaping these new ecosystems. The Carboniferous period, 359 million to 299 million years ago, was a time of unparalleled forest growth. Vast swamp forests covered large parts of the continents, especially in the northern land masses of Laurasia, and these forests would eventually form the immense coal deposits that power our world today. Amphibians diversified, and the first reptiles emerged, representing a key evolutionary step as they could lay their eggs on land, freeing them from aquatic dependence. This period also saw the assembly of the northern supercontinent of Euramerica, Laurasia, formed by the collision of Laurentia and Baltica, contributing to the unique conditions that allowed these massive forests to thrive. Atmospheric oxygen levels peaked, possibly contributing to the enormous size of some carboniferous insects. Finally, the Permian period, 299 million to 252 million years ago, was the culmination of the Paleozoic's geological and biological drama. By this time, Pangea was fully assembled, creating a single, vast landmass. Reptiles diversified rapidly, adapting to the varied environments of the new supercontinent. However, the very formation of Pangea brought about dramatic environmental changes. The immense continentality led to increasingly arid conditions in the continental interiors. Restricted ocean circulation patterns and the uplift of vast mountain ranges altered global climate profoundly. The Permian period ended with the greatest mass extinction event in Earth's history, the Permian-Triassic extinction event, often called the Great Dying. This catastrophic event, which wiped out 90% of marine species and 70% of terrestrial vertebrate species, is widely attributed to massive volcanic eruptions in Siberia, the Siberian Traps, which released vast amounts of greenhouse gases, triggering rapid global warming, ocean anoxia, lack of oxygen, and ocean acidification. The formation of Pangea itself, by concentrating land masses and influencing mantle dynamics, may have contributed to the conditions that led to this cataclysm. Throughout the Paleozoic, the Earth's environment underwent continuous and dramatic transformations. The climate shifted from periods of widespread marine environments and relatively stable temperatures to increasing continentality, with harsher extremes. Glacial periods, particularly in the Ordovician and Carboniferous, interrupted long stretches of warmer conditions. As Pangea formed, its vast size led to significant aridification in its interior. The atmosphere also changed, most notably with the significant rise in oxygen levels during the Carboniferous, due to the proliferation of vascular plants and massive forests, which contributed to the gigantic size of some arthropods. The oceans, too, were profoundly affected. Changes in ocean circulation patterns due to continental drift altered nutrient distribution and temperatures. As continents collided, seaways became restricted or closed entirely, influencing marine biodiversity and setting the stage for new evolutionary pathways. In conclusion, the Paleozoic era was not merely a prelude to Pangea's formation. It was a dynamic, tumultuous period where the very stage for the supercontinent's assembly was meticulously set. The inexorable march of plate tectonics, driven by the deep currents within Earth's mantle, saw the powerful entities of Gondwana and Laurasia engage in a protracted, slow-motion collision. This grand tectonic dance culminated in the formation of Pangea, a geological masterpiece that fundamentally reshaped Earth's geography, climate, and the trajectory of life. From the Cambrian explosion of marine life to the colonization of land by plants and animals, every major evolutionary milestone in the Paleozoic was intimately intertwined with the movements of these continental giants. The Paleozoic was an era of profound transformation, a testament to the Earth's ceaseless geological activity and the incredible resilience and adaptability of life in the face of such colossal change. The legacy of this era, and the slow dance of Gondwana and Laurasia, is etched into the very mountains we see today and forms the bedrock of our understanding of the planet's ancient, living history. Imagine the Earth's surface not as a solid, unmoving shell, but as a giant, ever-shifting jigsaw puzzle. This is the fundamental concept behind plate tectonics, a revolutionary idea that reshaped our understanding of our planet. The Earth's outermost layer, the lithosphere, is broken into several enormous pieces called tectonic plates. These plates are constantly, albeit slowly, in motion, gliding over the semi-fluid mantle beneath them. They interact in various ways, pulling apart at divergent boundaries, sliding past each other at transform boundaries, and perhaps most dramatically, smashing head-on at convergent boundaries. It is these head-on collisions, particularly between two continental masses, that are the true titans of Earth's geological processes, responsible for forging the colossal mountain ranges that mark the scars of ancient supercontinents. These immense forces of collision were the very architects of Pangea, shaping its vast bulk and leaving an enduring legacy in the landscapes we see today. When we talk about continental collisions, we're not just discussing a gentle nudge. These are events of truly unimaginable power occurring over millions of years. Unlike oceanic crust, which is dense and can be relatively easily pushed down or subducted into the Earth's mantle when it collides with another plate, continental crust is much thicker and more buoyant. It's like trying to force two enormous corks underwater. They simply won't go down easily. Instead, when two continental plates meet, the immense pressure causes the crust to buckle, fold, fracture, and pile up, much like a rug being pushed from opposite ends. This process of mountain building is known as orogeny, a term that speaks to the creation of these grand geological structures. The forces involved are so immense that they deform rocks on a truly staggering scale, creating intricate fold and thrust belts where layers of rock, once flat-lying sediments, are now contorted into dramatic arches and troughs, often stacked one upon another along massive fault lines. This shortening and thickening of the crust leads to the uplift of mountain ranges, often accompanied by intense heat and pressure that metamorphose existing rocks, transforming them into new types like slate, schist, and gneiss, which are hallmarks of these collision zones. The very roots of these mountains can extend dozens of miles deep into the Earth's mantle, a thickened keel of crust that helps support the colossal weight of the peaks above. This deep crustal root, in turn, influences processes like isostatic adjustment, where the mountains essentially float on the mantle, rising and falling over geological time as erosion removes material from their summits. One of the most compelling examples of a mountain range forged during the assembly of Pangea is the Appalachian Mountains in eastern North America. Today, these are generally lower, more rounded mountains compared to the jagged peaks of, say, the Himalayas. However, their present gentle contours belie a truly epic and violent past. The Appalachians were not formed by a single event, but by a series of colossal collisions that unfolded over hundreds of millions of years, culminating in the grand unification of Pangea. The final and most significant phase, known as the Alleghenian orogeny, was the direct result of the collision between what would become North America, then known as Laurentia, and the ancient supercontinent of Gondwana, specifically the portion that would later become Africa. Before the Alleghenian collision, there were earlier mountain-building events in the region, such as the Tectonic and Akkadian orogenies, which were linked to the closure of the ancient Iapetus Ocean and the accretion of volcanic island arcs and microcontinents onto Laurentia's eastern margin. These earlier events laid some of the groundwork, creating a complex continental margin that was ripe for the ultimate collision. But it was the Alleghenian orogeny, occurring roughly between 320 million and 280 million years ago, that represents the truly grand finale of Appalachian mountain building. During this period, the colossal landmass of Gondwana, carrying what is now Africa, pressed relentlessly against the eastern flank of Laurentia. The vast expanse of oceanic crust between them had already been subducted, but now continent met continent. The immense pressure from this convergence caused the pre-existing continental crust, including rocks from the earlier orogenies, and vast sequences of sedimentary rocks deposited in a subsiding basin along the margin, to be intensely folded, faulted, and thrust westward. Imagine immense slabs of rock, tens of miles thick, being pushed horizontally over one another for hundreds of miles. This is the essence of a thrust belt, and the Appalachians are a classic example. The Allegheny Front, a prominent escarpment running through parts of the Appalachian Range, marks the westernmost extent of significant deformation from this colossal collision. The scale of the Alleghenian orogeny was truly staggering. Geologists estimate that the ancient Appalachians, at their peak, might have rivaled the Himalayas in height, soaring perhaps as high as 25,000 or even 30,000 feet. This immense mountain chain stretched for thousands of miles, forming the central backbone of the newly formed Pangea. The evidence for this ancient grandeur is still visible today, even after hundreds of millions of years of relentless erosion. The characteristic parallel ridges and valleys that define much of the central and southern Appalachians are the eroded remnants of those immense folds and thrust faults. The metamorphic rocks found deep within the core of the mountains, such as schists and gneisses, bear testament to the intense heat and pressure they endured. Furthermore, vast quantities of clastic sediments, sandstones, shales, and conglomerates found in ancient basins to the west, known as foreland basins, represent the enormous volume of material eroded from these towering peaks over geological time. The sheer volume of these sedimentary deposits underscores the immense size and longevity of the mountain range. While the Appalachians represent the western part of Pangea's central mountain belt, The Ural Mountains in Russia provide another fascinating glimpse into the constructive power of continental collisions during the supercontinent's assembly. The Urals are a much narrower and generally lower range today, stretching for over 1,500 miles from the Arctic Ocean in the north to the Ural River in the south. Their formation, occurring roughly between 320 million and 250 million years ago, was a crucial event in the amalgamation of Pangea, specifically marking the suture zone where the ancient continent of Baltica, which would later become part of Europe, collided with the Siberian platform and the smaller continental fragments of the Kazakhstan bloc. This collision was complex, involving the closing of the Uralian Ocean, a relatively narrow seaway that once separated these land masses. As the ocean basin subducted, it ultimately led to the convergence and collision of continental crusts. The Urals, much like the Appalachians, are a classic example of a fold and thrust belt, with intensely deformed sedimentary, metamorphic, and igneous rocks. The linear nature of the range reflects the relatively narrow zone of intense compression. Unlike the Appalachians, which suffered extensive erosion in a humid climate, the Urals, located in a more arid and continental interior climate for much of their history, have retained some of their ruggedness, though they too have been significantly eroded. The geological characteristics of the Urals offer compelling evidence of their collisional origin. Ophiolites, which are fragments of oceanic crust and upper mantle that have been thrust onto continental crust during collision, are found in parts of the Urals, providing direct evidence of the ancient ocean that once existed there. The range is also renowned for its vast mineral riches, including gold, platinum, various base metals, and even gemstones. These deposits are often a direct consequence of the intense geological activity, including the circulation of hydrothermal fluids associated with the mountain building process. The immense heat and pressure during the collision created favorable conditions for the concentration of these valuable resources. The Urals, therefore, represent not just a physical boundary between Europe and Asia, but a fundamental geological suture, a line where once separate continental blocks were welded together to form the eastern part of the supercontinent Laurasia, which itself was a major component of Pangea. These two examples, the Appalachians and the Urals, are just prominent examples of the vast network of mountain ranges that were born from the powerful collisions during Pangea's formation. Another significant system, often referred to as the Hercynian or Variscan orogeny, stretched across much of Central and Southern Europe, from Spain and France through Germany and into the Czech Republic. This complex system of mountain belts was formed by the collision of various microcontinents and the supercontinent Gondwana with Laurasia. In a reconstructed Pangea, the Appalachians, the Hercynian system, and even parts of the Anti-Atlas Mountains in North Africa would have formed a continuous, colossal mountain chain running through the very heart of the supercontinent. This central Pangean mountain belt would have been a dominant topographical feature on Earth's surface for tens of millions of years, acting as a major climatic barrier and shaping weather patterns across the globe. The formation of Pangea through these relentless collisions had profound consequences beyond just the creation of towering peaks. The sheer scale of the landmass fundamentally altered global climate patterns. With such a vast continental interior, seasonal temperature extremes would have been far more pronounced. Much of the interior would have experienced arid or semi-arid conditions, leading to the formation of extensive deserts and the deposition of vast quantities of evaporate minerals. Conversely, the equatorial regions would have been characterized by widespread swamp forests, eventually giving rise to the immense coal deposits that are so economically important today. The assembly of Pangea also had a dramatic impact on ocean circulation patterns. The closing of ancient ocean basins and the formation of a single superocean, Panthalassa, would have significantly altered ocean currents, potentially influencing nutrient distribution, marine biodiversity, and global heat transport. Furthermore, the immense erosion of the newly formed mountain ranges would have delivered vast quantities of sediment and dissolved minerals into the oceans, potentially impacting ocean chemistry and marine life. In essence, the story of Pangea is a story of colossal collisions. It's about the relentless dance of Earth's tectonic plates, a dance that, over hundreds of millions of years, transformed a fragmented collection of continents into a single, magnificent supercontinent. The mountain ranges born from these collisions, like the Appalachians and the Urals, stand today as enduring monuments to this epic geological process. They are not merely picturesque landscapes. They are the very seams and scars of Earth's dynamic past, etched into the planet's crust, providing us with an incredible record of the immense forces that built a giant. The very act of their formation profoundly reshaped not only the topography of our planet, but also its climate, its oceanography, and the course of life's evolution. Understanding these tectonic collisions is crucial to grasping the immense scale and power of Earth's internal processes, and how they conspired to create the legendary supercontinent of Pangea, a truly unique chapter in our planet's long and fascinating history. It's a testament to the fact that Earth is not static. It is a living, breathing, ever-changing entity, with a deep and powerful history written in stone. The idea of a supercontinent like Pangea, where all of Earth's major land masses were once joined in a single, colossal entity, is a concept that still sparks wonder. But for it to move from an intriguing hypothesis to a widely accepted scientific theory, geologists needed concrete answers to fundamental questions. When did this grand union occur, and what evidence exists to prove it? The answers didn't come overnight. They were meticulously pieced together over decades of scientific inquiry, drawing upon a diverse array of geological and paleontological clues. The prevailing scientific consensus points to an estimated time of Pangea's full formation around 335 million years ago. This wasn't a singular, instantaneous event, but rather the culmination of millions of years of continental drift and a series of immense collisions that ultimately welded the major continental blocks into the cohesive landmass we recognize as Pangea. This particular date places the full assembly firmly within the Carboniferous period, a pivotal time in Earth's history, characterized by vast, swampy forests that would eventually form our planet's immense coal reserves. To pinpoint this precise moment of assembly, scientists had to become forensic detectives of the Earth, examining countless rock layers and ancient fossil records for clues. One of the most compelling lines of geological evidence comes from the study of paleomagnetism. This fascinating field relies on the fact that certain minerals in rocks, when they solidify from molten magma or are deposited as sediment, align themselves with Earth's magnetic field at that particular time. Imagine tiny compass needles frozen in time, pointing towards the magnetic pole of the past. By studying these ancient magnetic orientations from rocks of different ages on different continents, geologists can reconstruct the past positions of the continents relative to the magnetic pole. What they discovered was truly remarkable. When the data from various continents was plotted, their apparent polar wander paths, the seeming movement of the magnetic pole over time as viewed from a single continent, converged into a single consistent path when the continents were repositioned to form Pangea. This congruence of paleomagnetic data from widely separated landmasses was a powerful indicator that these continents were indeed once physically connected, forming a single entity whose unified magnetic signature could be traced through geological time. Furthermore, the ongoing study of magnetic anomalies on the seafloor, created as new oceanic crust forms at mid-ocean ridges and records reversals in Earth's magnetic field, provides irrefutable evidence that ocean basins have been opening and widening over millions of years. This seafloor spreading, in turn, necessitates that continents must have been moving apart, implying that at some point in the past they must have been much closer, if not entirely joined. Beyond the invisible magnetic evidence, the tangible proof from matching geological structures across now separated continents offered incredibly persuasive arguments for Pangaea's existence and the timing of its formation. One of the most striking examples involves the immense mountain ranges discussed earlier, such as the Appalachian Mountains in eastern North America. When reconstructed into Pangea, these mountains align perfectly with the Hercynian or Variscan mountain belt of central and southern Europe, and even connect with the Anti-Atlas Mountains of northwestern Africa. This forms a continuous, ancient mountain chain, the Central Pangean Mountain Belt, stretching across vast distances. The geological similarities are not just in their alignment, but also in their internal structure, the types of rocks found, and the evidence of intense folding and thrust faulting, all indicative of a single, shared collisional history. It's like finding matching seams on two different pieces of fabric that were once part of the same garment. The evidence doesn't stop there. The study of ancient cratons, the stable, ancient cores of continents, reveals how they fit together like puzzle pieces. For instance, the Canadian Shield of North America aligns remarkably well with parts of the Baltic Shield of Europe and the West African Craton. Furthermore, distinctive sequences of rock layers provide crucial stratigraphic evidence. One of the most compelling examples comes from the distribution of Carboniferous Permian glacial deposits. Geologists found evidence of ancient glaciations, including tillites, rock formed from consolidated glacial debris, glacial striations, scratches on bedrock left by moving ice, and U-shaped valleys scattered across southern South America, South Africa, India, Australia, and Antarctica. This pattern of ancient ice sheets makes no sense if the continents were in their present positions, as it would imply massive ice sheets forming in tropical and subtropical regions. However, when these continents are reassembled into the southern supercontinent of Gondwana, a major component of Pangea, they cluster around the South Pole, providing a logical explanation for the widespread glacial evidence. This was one of the earliest and most powerful pieces of evidence that propelled the theory of continental drift forward. In addition to glacial deposits, other paleoclimatic indicators embedded in the rock record support Pangaea's configuration. The vast coal swamps of the Carboniferous period, which laid down the immense coal deposits we mine today, are found on continents now widely separated, including North America, Europe, and parts of Asia. When Pangea is reconstructed, these coal deposits align along the equatorial belt, where conditions were ideal for the lush, tropical vegetation that formed them. Conversely, widespread deposits of evaporites, minerals formed by the evaporation of water, like salt and gypsum, and red beds, sedimentary rocks rich in iron oxides, indicating arid conditions, are found in the interior of reconstructed Pangea, perfectly consistent with the dry, continental climate that would have prevailed in such a vast landmass. The consistent distribution of these climatically sensitive rock types across the continents only makes sense if they were once part of a single, contiguous landmass, reinforcing the timing of Pangaea's full formation. While the geological evidence from rocks and magnetic fields is foundational, the fossil record provides some of the most charismatic and easily understandable proof for Pangaea's existence and the approximate timing of its assembly. Imagine ancient creatures, long extinct, whose remains tell a tale of connected continents. One of the most famous examples is the Glossopteris flora. This distinctive fern-like plant, with its tongue-shaped leaves, produced seeds too heavy to be dispersed widely by wind or water across vast oceans. Yet, fossils of Glossopteris are found abundantly in rock layers of the same age across South America, Africa, India, Australia, and Antarctica. The only plausible explanation for this widespread distribution is that these land masses were once connected, allowing the plant to spread across a continuous terrestrial environment. Another crucial piece of fossil evidence comes from the freshwater reptile Mesosaurus. This small aquatic reptile, about 3 feet long, lived exclusively in freshwater environments. Its delicate skeleton and freshwater habitat mean it could not have survived a journey across a vast saltwater ocean. However, Fossils of Mesosaurus are found in Carboniferous and Permian rocks, exclusively in two very specific regions, southern Africa and eastern South America. The restricted geographical distribution of this freshwater creature on continents now separated by the Atlantic Ocean is an incredibly powerful argument for their past connection, further bolstering the case for Pangea. Similarly, the land-dwelling reptile Lystrosaurus offers compelling evidence. This herbivorous, pig-sized creature, which lived during the late Permian and early Triassic periods, was a terrestrial animal, utterly incapable of swimming across oceans. Yet, its fossils are found across Antarctica, India, and South Africa. The presence of Lystrosaurus fossils on these three continents, now separated by thousands of miles of ocean, provides undeniable proof that these landmasses were once joined, forming part of a unified Pangea, particularly its Gondwanan component. The timing of these Lystrosaurus fossils aligns perfectly with the geological estimates of Pangea's existence. Finally, the distribution of Cynognathus, another land-dwelling reptile, roughly dog-sized, also points to the supercontinent. Fossils of Cynognathus have been found in South America and Africa. Like Lystrosaurus, this was a terrestrial animal that could not have traversed vast oceanic distances. Its presence on both continents reinforces the idea of a contiguous landmass in the past. Beyond these iconic examples, numerous other faunal and floral similarities have been observed across continents now separated, involving various ancient amphibians, other reptiles, and even early mammals. These widespread distributions of terrestrial species, which would have been unable to cross oceanic barriers, collectively tell a consistent story of a time when the continents were united. The beauty of this evidence lies in its convergence. No single piece of evidence stands alone. Instead, the independent lines of evidence, paleomagnetism, matching geological structures and rock sequences, paleoclimatic indicators, and the fossil record, all point to the same conclusion. Pangea existed, and it achieved its full formation around 335 million years ago. While geologists continue to refine the precise timing of certain collisional events and the exact configuration of some smaller blocks within Pangea, the overarching picture is robust and overwhelmingly supported by a wealth of scientific data. The assembly of Pangea at this estimated time was a monumental event that fundamentally reshaped the Earth. It led to a period of intense mountain building, dramatically altered global climate and ocean circulation, and profoundly influenced the evolution and distribution of life on the planet. The fossil evidence, in particular, gives us a tangible connection to this ancient world, allowing us to imagine a time when the animals and plants we study today roamed freely across land masses that are now separated by vast oceans. The story of Pangea is not just a tale of ancient geology. It's a testament to the dynamic nature of our Earth, a planet constantly in motion, constantly being reshaped by forces far grander than anything we can easily comprehend. The estimated time of its full formation, around 335 million years ago, is a crucial chapter in this ongoing narrative, a turning point that set the stage for the subsequent geological and biological evolution that would eventually lead to the world we inhabit today. It's a powerful reminder that the ground beneath our feet is not static, but is, and always has been, part of a grand planetary dance. Imagine a world where the journey from one coast to another would span continents, where the very concept of an ocean voyage between land masses was rendered moot by the sheer, monolithic presence of one colossal landmass. This was Pangea, the last legendary supercontinent of prehistory, a titan of land that dominated the Earth for tens of millions of years. And within this titanic landmass lay its very heart, a vast and forbidding expanse that dwarfed any desert known to our modern world. These were the central regions and inner deserts of Pangea, areas defined by their extreme distance from the moderating influence of any ocean, where the climate was a brutal symphony of heat, cold, and an almost ceaseless aridity. The sheer scale of Pangea fundamentally dictated its internal climate. Consider the enormity of it, a single landmass stretching from pole to pole, encompassing virtually all of the Earth's continental crust. This gargantuan expanse meant that vast tracts of land were located thousands of miles from any coastline. In today's world, even the largest continents like Asia or Africa have significant coastlines and internal regions that are not completely isolated from maritime moisture. But Pangea was different. The concept of continentality, the effect of a continental climate characterized by a greater range of temperature extremes and lower precipitation due to its distance from the moderating influence of the sea, was amplified on Pangea to an extent almost unimaginable today. Any moisture-laden air originating from the surrounding Panthalastic Ocean or the smaller Tethys Sea to the east would have been stripped of its humidity long before it reached the deep interior. As these air masses moved inland, they would encounter not just vast distances, but also formidable geographical barriers, further exacerbating the drying effect. One of the most significant topographical features contributing to the aridity of Pangea's heartland would have been its colossal mountain ranges. The very act of Pangea's formation, the slow, relentless collision of previously separate continental plates, created an extensive network of towering mountain belts. These included what we know today as the Appalachian Mountains in North America, the Scottish Highlands, and the Hercynian or Variscan Mountains of Europe and North Africa. When these continents converged to form Pangea, these mountain chains were lifted to truly majestic heights, perhaps rivaling or even exceeding the modern Himalayas in their early days. Imagine these mighty ranges running for thousands of miles across the supercontinent, forming an insurmountable barrier to atmospheric moisture. As prevailing winds, perhaps driven by nascent supermonsoon systems, attempted to carry rain clouds inland from the coasts, they would be forced upwards by these geological giants. The air would cool, condense, and release its moisture as precipitation on the windward side of the mountains, creating lush, if localized, environments. However, on the leeward side, the air would descend, warming and drying as it did so, creating vast, extensive rain shadows that stretched for thousands of miles into the continental interior. These rain shadows would have been the engines of aridity, transforming what might have been merely dry plains into colossal, unforgiving deserts. The nature of these inner deserts would have been varied, but consistently harsh. We can envision landscapes dominated by vast fields of sand dunes, not unlike parts of the Sahara or the Arabian Desert today, but on a scale that makes them seem small by comparison. These dunes, sculpted by constant winds, would have shifted and migrated over geological timescales, burying and revealing ancient landscapes. Beyond the rolling sands, there would have been immense rocky plains, barren plateaus, and vast, empty basins. Some of these basins might have held ephemeral lakes or inland seas during rare periods of increased precipitation, but as the water evaporated under the relentless sun, they would have left behind gleaming white salt flats, testament to the vanished moisture. The colors of these landscapes would have been predominantly reddish browns and oranges, derived from the iron oxides that formed as rocks weathered under the extreme temperatures and oxygen-rich atmosphere, creating the characteristic red beds that geologists identify as signatures of ancient desert environments. The evidence for these ancient deserts is abundant in the geological record. Extensive deposits of aeolian, wind-blown sandstones, evaporate minerals like gypsum and halite, and specific types of sedimentary structures indicative of arid environments. The temperature extremes in these central regions would have been staggering. With no large bodies of water to absorb and slowly release heat, the land would have heated up rapidly during the day, reaching scorching temperatures that would have been unbearable for most life forms. Conversely, at night, the absence of atmospheric moisture or thermal buffering would have allowed heat to radiate quickly into space, causing temperatures to plummet well below freezing. This extreme diurnal temperature range, coupled with vast seasonal fluctuations, brutally hot summers and bitterly cold winters defined the climate of Pangea's heartland. The air itself would have been thin and dry, often filled with dust churned up by powerful winds. Beyond the local effects of continentality and rain shadows, the very existence of Pangea would have dramatically altered global atmospheric circulation patterns. The enormous landmass would have created massive pressure differentials between the land and the surrounding Paleozoic ocean. This difference in heating and cooling rates would have driven colossal monsoon systems, far grander than anything we see today. During the summer months, the supercontinent would heat up intensely, creating a vast low-pressure system that would draw moisture-laden air from the ocean inwards. While some coastal regions might have experienced heavy seasonal rainfall during this period, the vast interior would likely have remained dry, as the rain-bearing winds would have dropped their moisture long before reaching the heartland. In winter, the land would cool rapidly, developing a high-pressure system that would push cold, dry air outwards. These seasonal wind shifts, though potentially bringing some moisture to the periphery, would have predominantly contributed to the dry conditions of the interior. This concept of a supermonsoon is a critical element in understanding Pangean climate, painting a picture of a planet with highly variable and extreme weather patterns, where the interior was perpetually starved of rain. The topography of Pangea was not just about the towering mountains. It was a tapestry woven from vast plains, extensive plateaus, and emerging rift valleys. While the Appalachian-Variscan mountain belt dominated the northern and central parts, other significant topographic features existed. Large, relatively flat plains and basins would have been interspersed between the mountain ranges. These basins, depending on their elevation and proximity to limited moisture sources, might have been sites of occasional inland seas or large, ephemeral lakes during periods of higher global temperatures and increased hydrological activity. However, for much of the time, these would have been arid basins, accumulating thick sequences of wind-blown sediments or evaporite deposits. As the Permian period progressed and Pangea itself began to experience the initial stresses that would eventually lead to its breakup, early signs of rift valleys would have begun to appear. These nascent rifts, where the continental crust was slowly stretching and thinning, would have created depressions that could potentially accumulate water, forming long, narrow lake systems, or become channels for intermittent river systems. Such rifts are often associated with volcanism, and while the major volcanic arcs would have been at the periphery of the supercontinent where subduction was occurring, some intracontinental volcanism might have been associated with early rifting, further shaping the landscape. The river systems of Pangea would have been equally extraordinary. Given the vastness of the landmass, enormous river networks would have been necessary to drain the continent. However, many of these rivers would not have reached the Paleozoic ocean. Instead, they would have terminated in the arid interior, flowing into inland basins and evaporating, forming playa lakes and salt flats. The few rivers that managed to reach the ocean would have been truly colossal, draining immense watersheds. The lack of multiple smaller continents and diverse ocean basins would have significantly influenced the global hydrological cycle. The volume of freshwater runoff into the Paleozoic ocean might have been less diverse in terms of sources, and its chemistry influenced by the extreme weathering in the interior of Pangea. Looking at the broader Pangean climate, the Permian period itself was characterized by generally higher atmospheric carbon dioxide levels than today. This would have contributed to a generally warmer Earth, but this warmth would not have been evenly distributed. The sheer size of Pangea led to pronounced thermal inertia for the landmass. It would take a long time to heat up and a long time to cool down. This created significant temperature gradients between the equator and the poles, as well as extreme seasonal variations. The poles, though connected by land, would have experienced severe winters, potentially with vast seasonal ice sheets, although the Permian was largely ice-free compared to earlier Carboniferous glaciations. Evidence for these climate zones comes from the distribution of ancient sedimentary rocks and fossils. For example, coal deposits, indicative of humid, swampy environments, are found in relatively narrow bands near the coasts, suggesting that the vast interior was unsuitable for such luxuriant vegetation. Conversely, widespread desert redbeds and evaporites dominate the central and subtropical latitudes. The Pangean climate, in essence, was a study in extremes. It was a world where the gentle, moderating hand of the ocean was largely absent from the continental heartland. It was a world of vast, arid interior deserts, colossal mountain ranges casting immense rain shadows, and atmospheric circulation patterns driven by the sheer thermal mass of the supercontinent. This harsh environment presented immense challenges for life, forcing evolution to craft species uniquely adapted to survive in a world that was, in many ways, utterly alien to our own. The geological remnants of this ancient heartland, preserved in the rocks of today's disparate continents, provide us with compelling evidence of a truly legendary and formidable land. The story of Pangea's climate and topography is not just a tale of ancient rocks and dry winds. It is a testament to the profound influence that continental configuration can have on the very lifeblood of a planet's climate system. The Permian period, spanning from roughly 299 million to 252 million years ago, was a time of profound transformation on Earth. It was the age when the supercontinent Pangea truly came into its own, reaching its greatest extent and fundamentally reshaping the planet's geography, climate, and consequently, its life. The story of Permian life is one of adaptation, diversification, and ultimately, the largest mass extinction event in Earth's history, a cataclysm that would reset the evolutionary clock and usher in the age of dinosaurs. To understand this period, we must delve into the dominant species and the unique environments they inhabited, and crucially, explore how the newly connected landmass of Pangea profoundly influenced these ecosystems, shaping the very fabric of life on Earth. At the dawn of the Permian, terrestrial ecosystems were still recovering from the Carboniferous coal swamp boom, dominated by giant insects and early amphibians. However, as the Permian progressed and Pangea assembled, the world grew drier and more seasonal, favoring new forms of life. When we look at the flora of the Permian, we see a significant shift. In the early Permian, especially in the more humid coastal regions and along river systems, remnants of the Carboniferous coal forests persisted. These included giant lycopods, like the tree-sized Lepidodendron and Sigillaria, sphenopsids, like calamites, giant horsetails, and a diverse array of ferns. These plants were well adapted to wet, swampy conditions, forming the vast peat deposits that would eventually become the coal seams we mine today. However, as the climate of Pangea became increasingly arid and seasonal, these moisture-dependent plants began to decline in dominance, replacing them with the gymnosperms, an evolutionary breakthrough that allowed plants to colonize drier environments. Gymnosperms, such as conifers, cycads, and ginkgos, had several key adaptations that gave them a competitive edge. Their seeds, unlike the spores of ferns and lycopods, contained a food reserve and a protective coating, allowing them to withstand periods of drought and germinate when conditions were favorable. Their pollen, carried by the wind, eliminated the need for water for reproduction, freeing them from proximity to standing water. Furthermore, their leaves were often tougher, needle-like, or leathery, reducing water loss through transpiration. A particularly significant example of Permian flora, especially in the southern supercontinent of Gondwana, which was part of Pangea, was the Glossopteris flora. Glossopteris was a seed fern, a group that bridged the gap between ferns and true seed plants. Its distinctive tongue-shaped leaves and seeds borne in cupules were incredibly widespread, forming vast forests across what is now South America, Africa, India, Antarctica, and Australia. The global distribution of Glossopteris fossils was one of the key pieces of evidence that Alfred Wegener used to propose his theory of continental drift, a precursor to our understanding of plate tectonics and Pangea. These Glossopteris forests were a vital part of the Permian ecosystem, providing the primary food source and habitat for many herbivores. On the faunal side, the Permian was truly the age of the synapsids, often referred to as mammal-like reptiles. These creatures were the dominant terrestrial vertebrates of the period, showcasing an incredible array of forms and ecological roles. They were not true reptiles in the modern sense, but rather a lineage that diverged before the reptile-mammal split, giving rise to mammals later. In the early Permian, the pelycosaurs were prominent. These were relatively primitive synapsids, with iconic examples like Dimetrodon, famous for its large sail-like fin on its back. While its exact function is still debated, the sail is thought to have played a role in thermoregulation, absorbing heat to warm up quickly, or radiating excess heat to cool down, or possibly display. Pelycosaurs were diverse, ranging from large carnivores to smaller insectivores. As the Permian progressed, the pelycosaurs were largely replaced by the more advanced therapsids. These were a more diverse and successful group of synapsids, showing increasingly mammal-like features, such as more efficient jaw musculature, differentiated teeth, and limb postures that allowed for more efficient locomotion. The therapsids truly ruled the Permian land. Among the therapsids, several groups stand out. The dinocephalians were large, often formidable creatures, some of the largest land animals of their time. They included both massive herbivores with thick skulls, like Esteminosuchus, which had bony protuberances on its head, and impressive carnivores, like Ankylosaurus, a powerful predator. Their remains are primarily found in South Africa and Russia, showcasing their widespread distribution across Pangea. Perhaps the most abundant and ecologically significant therapsids were the dicynodonts. These tusked, often stout-bodied herbivores ranged in size from small, dog-like burrowers to large, hippopotamus-sized grazers. They possessed a distinctive beaked skull with two tusks, hence dicynodont, meaning two dog teeth, well suited for cropping tough vegetation. Their widespread distribution across Pangea, particularly the iconic Lystrosaurus, whose fossils are found on every Gondwanan continent, Africa, Antarctica, India, Australia, South America, is another powerful testament to the interconnectedness of the Permian landmass. Their burrowing habits, inferred from skeletal adaptations, likely allowed them to survive periods of drought and escape extreme temperatures. The top predators of the Permian were the Gorgonopsians, a group of fearsome, saber-toothed therapsids. With powerful jaws and long, dagger-like canine teeth, they were built for hunting larger prey. Examples like Gorgonops and Inostrancevia would have been the apex predators of their ecosystems, preying on the numerous dicynodonts and other herbivores. While synapsids dominated, reptiles, sauropsids, were also present and beginning to diversify, setting the stage for their explosive radiation in the Triassic. Large, heavily armored herbivorous reptiles, like the pariasaurs, e.g. Scutosaurus, lumbered across the Permian landscapes, resembling a cross between a turtle and an armadillo. Smaller, more agile, lizard-like forms like the procolophonids were also common. Crucially, the ancestors of dinosaurs and crocodiles, the archosauromorphs, began to make their appearance in the late Permian, though they were still relatively small and inconspicuous compared to the dominant therapsids. Amphibians, though declining in overall dominance due to the drier climates, were still present in wetter areas, with large temnospondyls continuing to thrive in aquatic and semi-aquatic environments. Insects continued to be diverse, with early beetles, cockroaches, and large dragonflies populating the skies and undergrowth. So, how did the connected landmass of Pangea fundamentally influence these ecosystems? The impact was profound, manifesting in several key ways. Firstly, and perhaps most significantly, the formation of Pangea led to the homogenization of terrestrial biota. With virtually all of the Earth's continental crust joined together, there were no major oceanic barriers to prevent the dispersal of species across vast distances. Animals could migrate freely across the supercontinent, and plants could spread their seeds and spores widely. This led to a reduction in provincialism, the degree to which species are restricted to specific geographic regions. In a world fragmented by oceans, distinct species evolve on isolated continents. On Pangea, however, the same or very closely related species could be found across what are now widely separated landmasses. The classic examples of Glossopteris flora and Lystrosaurus fauna mentioned earlier are irrefutable evidence of this homogenization. The ability of these organisms to spread across such vast distances, leaving their fossil remains on continents now thousands of miles apart and separated by oceans, underscores the profound impact of Pangea's unity. This broad distribution meant that, for a given climate zone, similar ecosystems could develop across the entire supercontinent, reducing regional biological distinctiveness. Secondly, Pangea's vastness created broad and extreme climatic zones, forcing life to adapt to a wide range of conditions. As discussed, the interior was dominated by arid deserts, while coastal regions might have experienced more moderate or monsoon-driven climates. This climatic zonation led to evolutionary pressures favoring adaptations for survival in these diverse environments. Gymnosperms, with their drought-resistant features, thrived in the drier, more seasonal interior and subtropical zones. In contrast, the more primitive, moisture-dependent coal forest plants were relegated to the narrower bands of humid coastal plains or localized rift valley systems where water was more abundant. Animals, too, had to adapt. Many Permian synapsids, like the dicynodonts, likely developed strategies for coping with aridity, such as burrowing or specialized diets. The sheer scale of these climatic zones meant that adaptations for one zone could be applied across a truly continental scale. Thirdly, the connected land facilitated widespread migration and dispersal. Animals were not confined to isolated islands or continents. They could potentially travel immense distances in response to changing environmental conditions, availability of food sources, or to escape predators. While this freedom of movement might have led to increased competition in some areas, it also allowed species to track suitable habitats as climate zones shifted over geological time. For instance, if a particular region became too arid for a certain herbivore, it could potentially migrate to a more favorable, wetter region thousands of miles away within the same supercontinent. This widespread dispersal could also have influenced predator-prey dynamics on a continental scale, with top predators potentially ranging across vast territories in search of their prey. Fourthly, the unification of land masses might have contributed to that reduced speciation through allopatry. Allopatric speciation, where populations are geographically isolated, e.g. by oceans or mountain ranges, and evolve independently into distinct species, is a major driver of biodiversity. With Pangea, these major isolating barriers were removed for terrestrial life. While local geographical features like rivers and smaller mountain ranges would still have existed, the absence of vast oceanic divides meant that populations were more likely to remain interconnected over immense distances. This could have resulted in a lower overall global biodiversity compared to periods when continents were fragmented, as there were fewer opportunities for distinct species to evolve in isolation. While individual species might have been incredibly widespread, the total number of distinct species on Earth might have been comparatively lower than in periods with multiple separated continents. Fifthly, the existence of Pangea fostered the ecological dominance of terrestrial forms. With such an enormous landmass, terrestrial ecosystems developed an unprecedented scale and complexity. Evolutionary innovation in the Permian was largely driven by the challenges and opportunities presented by this vast terrestrial realm. The dominance of the therapsids and the rise of gymnosperms highlight this trend. The sheer amount of available land meant that a greater proportion of Earth's biomass and biodiversity resided on land, shifting the evolutionary focus away from purely marine environments, although marine life was still incredibly rich. Finally, And somewhat ironically, while the connected land facilitated dispersal, it also meant that widespread environmental changes could impact species across a much larger area, potentially contributing to the severity of the Permian Triassic extinction event. A single, massive, and potentially unstable global climate system driven by the supercontinent's configuration meant that a catastrophic event, like the massive volcanic eruptions of the Siberian traps at the end of the Permian, could have had repercussions across the entire landmass. The interconnectedness that allowed species to spread also meant that there were fewer refugia, or safe havens, for species when conditions turned catastrophic. If a warming trend, driven by volcanic CO2 emissions, led to widespread aridity, there were few isolated, verdant pockets of land left untouched. This vulnerability, inherent in a homogenized, supercontinental ecosystem, likely played a role in the unparalleled devastation of the Permian Triassic extinction, which wiped out an estimated 90% of marine species and 70% of terrestrial vertebrate species. In conclusion, Permian life and ecosystems were inextricably linked to the existence of Pangea. The supercontinent's formation orchestrated a profound shift in global climate, favoring adaptations for aridity and seasonality. It led to the widespread dominance of groups like the mammal-like reptiles and gymnosperms, creatures superbly adapted to this new world. And most importantly, it reshaped the very patterns of biodiversity, leading to a period of biological homogenization and widespread distribution, but also a period of vulnerability that would ultimately culminate in the greatest mass extinction event in Earth's history. The legacy of Permian life on Pangea is not just a story of ancient creatures, but a powerful illustration of how the grand forces of plate tectonics can sculpt the environments and dictate the evolutionary paths of life on Earth. Imagine, if you will, a world that, for a time, seemed to teeter on the brink of absolute biological collapse. This wasn't some fleeting catastrophe, a localized event, but a global cataclysm that redefined life on Earth, stripping away 90% of all marine species and approximately 70% of terrestrial vertebrate species. This apocalyptic episode, etched into the planet's history around 252 million years ago, is starkly known as the Permian Triassic extinction, or more dramatically, the Great Dying. It stands as the most profound and devastating extinction event in Earth's entire 4.5 billion-year saga, a true bottleneck that the planet's biosphere struggled for millions of years to recover from. To understand the sheer scale of this tragedy, we must first set the stage, visualizing the world that existed just before this cataclysm struck. The late Permian period was a time dominated by the supercontinent Pangea, a colossal landmass that stretched from pole to pole, exerting an unparalleled influence on global climate and ocean circulation. This singular continental configuration meant that vast interiors of Pangea were characterized by extreme aridity, far from the moderating influence of the ocean. Coastal regions, however, experienced more temperate or monsoonal climates. Life was flourishing, especially within the marine realm, which boasted a rich diversity of invertebrates, including ammonoids, brachiopods, bryozoans, and a staggering array of corals. On land, an impressive menagerie of synapsids, often referred to as mammal-like reptiles, but truly distinct and fascinating creatures in their own right, roamed the terrestrial ecosystems. These included the mighty gorgonopsids, formidable predators, and the abundant dicynodonts, such as the iconic Lystrosaurus, who were herbivorous and often tusked. Forests of conifers, cycads, and ferns dominated the landscapes, supporting a complex web of life that had been evolving for tens of millions of years. The world, though perhaps a bit starker and less diverse than the one we inhabit today, was nonetheless teeming with life, a vibrant tapestry woven over deep time. Yet, beneath this veneer of stability, geological forces of unimaginable power were stirring, poised to unleash an ecological nightmare. The prime suspect, The overwhelming and most widely accepted culprit behind this global devastation points firmly to an extraordinary outpouring of volcanism in what is now Siberia. Known as the Siberian Traps, this vast igneous province represents a true geological anomaly, a place where the Earth's mantle disgorged an unprecedented volume of magma onto the surface. Imagine volcanic eruptions not as localized cones spewing ash, but as fissures in the Earth's crust, hundreds of kilometers long, gushing rivers of molten rock, day after day, year after year, for what might have been as long as 1,000,000 years. The sheer scale of the Siberian Traps is almost incomprehensible. Estimates suggest that several million cubic kilometers of basaltic lava poured out, forming layers of rock up to thousands of meters thick. These weren't gentle flows. While flood basalts are often characterized by relatively quiet eruptions, the immense volume of gas released during such a prolonged event would have had cataclysmic global effects. The eruptions occurred in pulses, with massive effusions of basaltic lava interspersed with explosive phases. Crucially, these eruptions were not just spewing lava, they were releasing gargantuan quantities of volatile gases into the atmosphere. The primary drivers of climate change were carbon dioxide, a potent greenhouse gas, and sulfur dioxide, which initially causes cooling by forming aerosols that reflect sunlight. However, over the immense timescales of these eruptions, the warming effect of carbon dioxide would have utterly dominated. In addition to these, the magma interacted with vast deposits of coal, hydrocarbons, and evaporites, salt deposits, in the underlying crust. This interaction acted like a global oven, baking these organic-rich sediments and releasing even more devastating compounds: methane, an even more potent greenhouse gas than carbon dioxide, chlorine, and fluorine. The sustained release of such an array of planet-altering gases transformed the Earth's atmosphere, triggering a cascade of environmental collapses that spiraled out of control. The immediate atmospheric and climate consequences of this colossal volcanic outpouring were multifaceted and horrific. While a brief, initial cooling period might have occurred due to the release of sulfur aerosols, a sort of volcanic winter, this effect would have been ephemeral, soon overwhelmed by the sustained and massive injection of greenhouse gases. The relentless release of carbon dioxide and methane into the atmosphere initiated a runaway global warming scenario. Global temperatures would have soared by several degrees Celsius, perhaps even more than 10 degrees Celsius, across the planet. This was not a gradual warming. It was rapid on geological timescales, too quick for most life forms to adapt. Imagine a world where temperatures rose so dramatically that tropical regions became virtually uninhabitable, where deserts expanded, and where the delicate balance of ecosystems was utterly shattered. On land, this would have led to widespread droughts, changes in precipitation patterns, and increased aridity in regions that once supported lush forests. This climate upheaval would have stressed terrestrial vegetation, making them more vulnerable to disease, fires, and the indirect effects of a drastically altered atmosphere. However, the true horror of the Great Dying wasn't confined to the land. The oceans bore the brunt of the catastrophe, becoming a toxic cauldron of death. As global temperatures rose, the solubility of oxygen in seawater plummeted. Warmer water simply holds less dissolved gas, including the oxygen vital for marine life. Simultaneously, the influx of vast amounts of carbon dioxide from the atmosphere dissolved into the oceans, leading to a phenomenon known as ocean acidification. This decrease in pH would have made it incredibly difficult for marine organisms that build shells or skeletons out of calcium carbonate, such as corals, mollusks, and many planktonic organisms, to survive, as their ability to form and maintain these structures was severely hampered. The combination of rising temperatures and oxygen depletion set in motion a devastating sequence of events within the marine realm. One of the most terrifying consequences for the oceans was the widespread development of ocean anoxia and, even worse, euxinia. As oxygen levels in the surface waters dwindled and with warmer temperatures causing the ocean layers to stratify, preventing the mixing of oxygen-rich surface waters with oxygen-depleted deep waters, vast areas of the ocean became anoxic, utterly devoid of oxygen. This wasn't just restricted to the deep ocean. The anoxic zones spread upwards, encroaching into shallower waters, suffocating anything in their path. But it didn't stop there. In these anoxic conditions, a particular type of anaerobic bacteria, known as green sulfur bacteria, began to thrive. These bacteria produce hydrogen sulfide, H2S, a highly toxic gas that gives off a characteristic rotten egg smell. When hydrogen sulfide accumulated in sufficient quantities, the oceans became euxinic, a state where both anoxia and high concentrations of hydrogen sulfide prevail. Evidence from sedimentary records across the globe, showing layers of black shales rich in organic matter and sulfur isotopes, strongly supports the widespread occurrence of euxinia. Imagine a world where the oceans turned black, emitting a pervasive noxious odor, and where the water itself became poisonous to most aerobic life forms. The effects of ocean anoxia and euxinia were catastrophic. Marine animals, from microscopic plankton to large predators, were either poisoned directly by the hydrogen sulfide or suffocated by the lack of oxygen. The shallowing of the thermocline, the boundary between warm surface water and cooler, deeper water, pushed the toxic, oxygen-depleted waters closer to the surface, wiping out vast populations in what were once thriving shallow marine ecosystems. It's even hypothesized that the escaping hydrogen sulfide gas from the oceans could have accumulated in the atmosphere, directly poisoning terrestrial life and destroying the ozone layer, exposing land organisms to lethal levels of UV radiation. This grim possibility suggests a terrifying feedback loop, where the degradation of the oceans further compounded the devastation on land. Beyond the direct volcanic emissions and their immediate climatic impacts, other contributing factors and terrifying feedback loops may have exacerbated the crisis. The initial warming could have triggered the release of vast quantities of methane from methane clathrates, ice-like cages of methane trapped in permafrost and deep-sea sediments. Methane, as mentioned, is a far more potent greenhouse gas than carbon dioxide, capable of causing rapid and dramatic temperature spikes. This release would have acted as an amplifying feedback loop, further accelerating the global warming trend and pushing the Earth's climate system past critical tipping points. While less emphasized than volcanism, some theories also suggest widespread wildfires could have played a role, potentially driven by drought conditions and altered atmospheric compositions, although this is less central to the leading hypothesis. Changes in ocean circulation patterns, themselves a consequence of rising temperatures, would have further exacerbated the spread of anoxia and prevented the replenishment of oxygen-rich waters, trapping the oceans in a deadly cycle. The scale of devastation was truly unprecedented. The statistics are chilling. 90% of marine species and 70% of terrestrial vertebrate species simply vanished. Entire groups of organisms that had thrived for millions of years were completely wiped out. The trilobites, iconic arthropods that had graced the ocean since the Cambrian period, finally disappeared. Blastoids, a group of stalked echinoderms related to sea lilies, also met their end. Many families of brachiopods, ammonoids, and crinoids suffered catastrophic losses, leading to their complete disappearance or severe reduction in diversity. On land, the mighty gorgonopsids were eliminated, and while some dicynodonts like Lystrosaurus survived, the vast majority of synapsids were wiped out. The ecosystems of the late Permian were utterly dismantled, leaving behind a biological wasteland. This event demonstrated a grim extinction selectivity, meaning some groups were more vulnerable than others. Organisms with low metabolic rates, or those that could withstand periods of anoxia, or perhaps those with adaptations to warmer, more acidic waters, might have had a slightly higher chance of survival, though the overall picture was one of widespread obliteration. The aftermath of the Great Dying was a period of profound biological emptiness. The early Triassic, the period immediately following the extinction, is often referred to as a dead zone or a Lilliput effect, referring to the significantly smaller size of surviving organisms compared to their Permian ancestors. Ecosystems were simplified, dominated by a few disaster taxa, generalist species that could tolerate extreme conditions, like the ubiquitous Lystrosaurus. It took millions of years for biodiversity to even begin to recover, a stark reminder of the long-term consequences of such a profound environmental collapse. The recovery was not a simple return to the old ways. Instead, it ushered in a new age, creating ecological vacuums that would eventually be filled by novel life forms. This agonizingly slow recovery period, however, set the stage for the emergence of some of the most iconic creatures in Earth's history, paving the way for the rise of the dinosaurs and, much later, the mammals. Current research continues to refine our understanding of the Great Dying. Scientists are actively investigating the precise timings of different volcanic pulses and their correlation with extinction spikes, analyzing ancient sediments for geochemical markers that reveal past ocean conditions, and using sophisticated climate models to simulate the various environmental scenarios. Debates continue about the exact sequence of events and the relative importance of each causal mechanism, but the consensus firmly points to the Siberian Traps volcanism as the ultimate trigger, initiating a catastrophic cascade of environmental changes that led to the most devastating mass extinction event our planet has ever witnessed. It serves as a sobering reminder of the Earth's dynamic systems and the profound impact that sudden, extreme geological events can have on the trajectory of life. The Great Dying was not just an end. It was a violent reset, a tabula rasa upon which a new chapter of life's evolutionary story would slowly, painstakingly, be written. The Triassic period, spanning from approximately 252 million years ago to 201 million years ago, represents a fascinating and often overlooked chapter in Earth's deep history. It began in the smoldering ashes of the Permian Triassic extinction, a world dramatically emptied of its former inhabitants, and ended with another significant extinction event, though less severe, that nevertheless cleared the stage for the undisputed reign of the dinosaurs. This period, therefore, was one of immense biological innovation, a time when the planet's ecosystems, having endured the ultimate biological reset, began a slow, often faltering, but ultimately successful journey towards recovery and the emergence of entirely new forms of life, including the first dinosaurs and our own distant mammal ancestors. It was truly an age of new beginnings, where ecological niches, once filled by a multitude of now extinct creatures, lay wide open, inviting rapid diversification and evolutionary experimentation. The world of the Triassic period was still dominated by the supercontinent Pangea. For much of the Triassic, this immense landmass remained largely intact, stretching across the globe, influencing climates in profound ways. The vast interior of Pangea was characterized by hot, dry conditions, with extensive deserts forming far from the moderating influence of the oceans. However, evidence suggests strong monsoonal patterns prevailed in certain coastal regions, bringing seasonal rainfall. The geological record indicates generally high global temperatures throughout the Triassic, without the polar ice caps we see today. This widespread warmth had significant implications for both marine and terrestrial life, shaping the distribution of plants and animals. While the land was baking in the sun, the oceans were slowly recuperating from the Great Dying, but still relatively warm and less oxygenated than before. Vegetation, too, had undergone a dramatic transformation. After the Permian devastation, the early Triassic saw a temporary simplification of terrestrial floras, dominated by a few hardy, fast-growing plants like the fern Pleuramea. However, by the mid and late Triassic, forests of conifers, cycads, palm-like plants, and ginkgos began to re-establish themselves, providing the foundation for more complex ecosystems. The immediate aftermath of the Permian Triassic extinction saw a greatly simplified biosphere. A few tenacious groups of organisms, often referred to as disaster taxa, managed to survive the cataclysm, and, in the early Triassic, often dominated the impoverished ecosystems. The most famous example of a terrestrial disaster taxon is the dicynodont Lystrosaurus. This pig-sized, tusked synapsid was an herbivore and seemingly incredibly resilient. Its fossils are found in vast numbers across what was once Gondwana, southern Pangea, from Antarctica to South Africa, India, and China, earning it the nickname the Triassic Ark. Its ecological success in the immediate aftermath of the extinction is attributed to its generalist diet, burrowing capabilities, and potential ability to tolerate low oxygen levels. Lystrosaurus dominated the early Triassic landscape for a few million years, a stark testament to the extent of the prior extinction, a world where one hardy survivor became globally ubiquitous simply because so many competitors had vanished. However, as the Triassic progressed, the biological recovery gained momentum, and new evolutionary avenues were explored. Among the most significant developments was the rise of the archosauromorphs. This diverse group of reptiles included the ancestors of modern crocodiles and birds, and, crucially, the dinosaurs. In the early Triassic, various forms of archosauromorphs began to radiate, capitalizing on the open ecological niches. Many of these early archosauromorphs were small, lizard-like creatures, but they possessed key adaptations that would prove advantageous: more efficient respiration systems and improved locomotor abilities, particularly the trend towards more upright stances. These innovations set the stage for their eventual dominance. The first true dinosaurs emerged relatively late in the Triassic period, around 230 million years ago. For a long time, they were not the dominant terrestrial animals. That role was largely held by other groups of archosauromorphs, particularly the pseudosuchians, crocodile-line archosaurs, and, to a lesser extent, the synapsids, mammal ancestors. Early dinosaurs were typically small, agile, and bipedal. Key examples from this period include Eoraptor, Herrerasaurus, and Staurikosaurus, all discovered in the famous Ischigualasto Formation in Argentina, a veritable treasure trove of late Triassic fossils. These early forms were not giants, but they were nimble predators, perhaps no larger than a modern human. Their teeth suggest they were carnivorous, preying on smaller animals, or perhaps scavenging. Their bipedal stance allowed for increased speed and agility, leaving their forelimbs free for grasping or manipulation. The question of their immediate ancestors within the archosauromorph tree is a complex one, still debated among paleontologists. However, it is clear that dinosaurs evolved from a lineage within the Archosauria, distinguishable by specific anatomical features, such as a perforated hip socket, allowing for a more upright, erect limb posture, and a specialized ankle joint. These seemingly minor anatomical innovations were profoundly significant. An erect posture, where legs are positioned directly underneath the body rather than splayed out to the sides, allows for more efficient locomotion, making running and sustained movement less energetically costly. This was a key advantage in the competitive landscape of the late Triassic. Their hollow bones, while not yet as pronounced as in later birds, also contributed to a lighter, more efficient skeleton. Despite these advantages, early dinosaurs were often overshadowed by their pseudo-Sushian cousins, who, for much of the Triassic, occupied the top predatory niches and herbivorous roles. Creatures like the phytosaurs, crocodile-like aquatic predators, aetosaurs, armored, herbivorous reptiles, and the formidable rauisuchians, large terrestrial predators resembling crocodiles on land, were the undisputed kings of the Triassic landmasses. Dinosaurs were still relatively rare and perhaps ecologically marginal players for a significant portion of the period. While the dinosaurs were making their first tentative steps onto the evolutionary stage, another crucial lineage was also undergoing a silent but profound transformation: the synapsids, our very own mammal ancestors. Recall that synapsids, often mistakenly called mammal-like reptiles, were the dominant terrestrial vertebrates in the Permian period. The Great Dying had decimated their ranks, but a few lineages survived, particularly the cynodonts, and a handful of dicynodonts, like Lystrosaurus, which we already discussed. The evolutionary journey of the cynodonts through the Triassic is a story of gradual but consistent change, accumulating increasingly mammal-like features. Cynodonts began to show significant innovations in their dentition. They developed specialized teeth, including incisors for nipping, canines for piercing, and molars for grinding, indicating more efficient food processing. This was a major departure from the more uniform, peg-like teeth of earlier reptiles. Another key development was the formation of a secondary palate, a bony plate that separates the nasal passage from the mouth cavity. This allowed cynodonts to breathe while chewing, a critical adaptation for active, higher metabolism animals. The bones of the lower jaw also underwent reorganization, leading to the eventual incorporation of some jaw bones into the middle ear, a defining characteristic of mammals. Examples like Thrinaxodon and Cynognathus illustrate these intermediate stages, creatures that were clearly reptilian in many respects, but undeniably trending towards mammalian characteristics. They were likely endothermic, warm-blooded, or at least evolving towards it, which would have provided a significant advantage in the varied and often challenging climates of Triassic Pangea. The presence of whiskers, indicative of fur, is also inferred for some cynodonts, suggesting that they were already developing hair for insulation. By the very late Triassic, these evolutionary changes culminated in the emergence of the first true mammals. These earliest mammals were typically very small, often no larger than modern shrews, and likely nocturnal. Their small size and nocturnal habits probably allowed them to avoid direct competition with the larger, more dominant archosaurs. They occupied ecological niches that the larger reptiles couldn't exploit, focusing on insects and other small invertebrates. While they lived alongside the towering dinosaurs, they were not in their shadow in the sense of being subordinate. Instead, they were carving out their own evolutionary path, developing the unique suite of mammalian characteristics, endothermy, lactation, advanced hearing, and larger brains relative to body size, that would eventually allow them to diversify and flourish after the dinosaur era. The Triassic was a dynamic period of intense ecological competition and coexistence. For much of the period, the Pseudosuchians were the undisputed kings of the land. The phytosaurs, resembling modern crocodiles, dominated the rivers and lakes as apex predators. Atosaurs, with their heavy armor, were common herbivores, while the swift and formidable Rauisuchians, like Postosuchus, were the top terrestrial predators, often much larger than the contemporary dinosaurs. Early dinosaurs, for their part, were still small and relatively unspecialized. They coexisted with these dominant groups, possibly filling more generalized or marginal roles, perhaps as opportunistic predators or omnivores in areas less favored by the larger archosaurs. The stage was set for a grand evolutionary drama, with various reptile lineages vying for supremacy in a recovering world. The transition from the Triassic to the Jurassic period, around 201 million years ago, was marked by another significant, though less severe, extinction event, the Triassic-Jurassic extinction. This event is widely believed to have been triggered by massive volcanic eruptions associated with the breakup of Pangea and the formation of the Central Atlantic Magmatic Province, CAMP. These colossal eruptions, akin to a smaller-scale Siberian traps event, released vast amounts of carbon dioxide and sulfur dioxide, leading to rapid global warming, ocean acidification, and widespread environmental disruption. This event significantly impacted the dominant groups of the late Triassic. The Pseudosuchians, which had ruled for tens of millions of years, suffered massive losses. Most of the large atosaurs, phytosaurs, and Rauisuchians vanished. Crucially, the dinosaurs, for reasons still debated, but likely linked to their specific adaptations, perhaps their superior locomotion, or specific dietary generalism, or simply sheer luck, navigated this extinction event relatively unscathed. While some early dinosaur lineages did go extinct, the core groups that would dominate the Jurassic survived. This differential survival was a pivotal moment in Earth's history. With their primary competitors largely removed from the ecological stage, dinosaurs were freed from the constraints that had limited their size and diversity throughout the Triassic. This opened up an unprecedented opportunity for rapid diversification and adaptive radiation. Within a few million years into the Jurassic, dinosaurs had diversified into the enormous sauropods, the formidable theropods, and a host of other iconic forms that would define the Mesozoic era. The Triassic, therefore, was not just a recovery period. It was the crucial crucible in which the stage was set for the age of dinosaurs. It laid the foundation for the incredible evolutionary explosion that would follow, a legacy of profound change that shaped the future of life on Earth. Our understanding of the Triassic period and the emergence of early dinosaurs and mammal ancestors has been tremendously advanced by paleontological discoveries around the globe. The fossil beds of the Ixigualasto Formation in Argentina, for example, have provided an unparalleled window into the late Triassic, yielding some of the most complete specimens of early dinosaurs like Herrerasaurus and Eoraptor. Similarly, fossil sites in South Africa have been instrumental in unraveling the evolutionary story of the cynodonts and other synapsids, illustrating their gradual journey towards mammalian characteristics. Discoveries in North America, particularly the Chinle Formation, have provided insights into the diverse array of Triassic reptiles that coexisted with early dinosaurs. Each new fossil find, whether a fragment of bone or a complete skeleton, contributes to the ever-evolving puzzle of this pivotal geological period. Scientists are constantly re-evaluating existing evidence, applying new technologies, and refining our understanding of these ancient ecosystems. The Triassic remains a testament to the remarkable resilience of life, its ability to recover from unimaginable devastation, and its endless capacity for evolutionary innovation, ultimately giving rise to some of the most iconic and enduring lineages on our planet. Imagine a world so vast, so interconnected by land, that you could theoretically walk from the South Pole to the North Pole without once getting your feet wet from an ocean crossing. This was Pangea, the colossal supercontinent that dominated Earth's geography for hundreds of millions of years, from the late Paleozoic through the early Mesozoic eras. Its sheer size, an unprecedented accumulation of nearly all the planet's landmass, didn't just redefine the map. It profoundly reshaped the very fabric of Earth's climate. Forget the familiar fragmented continents and oceans of today, each with its localized weather patterns. Pangea operated on a grander, more monolithic scale, fostering a climate that was extreme, dynamic, and utterly unique, characterized by a dramatic contrast between its parched, unforgiving interior and its relatively more hospitable coastal fringes. Understanding Pangea's climate isn't just about ancient weather. It's about appreciating the immense power of continental configuration to dictate global atmospheric and oceanic circulation, shaping ecosystems and influencing the very trajectory of life on Earth. The most striking feature of Pangea's climate was undeniably its vast, arid interior. Picture it, a continental expanse so wide that moisture-laden winds, having traversed vast stretches of ocean, would simply lose their capacity to carry water vapor as they moved inland. By the time these air masses reached the heart of Pangea, they would have shed most of their moisture, leaving behind an immense rain shadow stretching for thousands of miles. This wasn't just a desert, it was a super desert, a scale of aridity almost unimaginable in our modern, more fragmented world. The core of Pangea, particularly in regions that would eventually become parts of North America, Africa, and South America, was a realm of perpetual drought. The landscape would have been dominated by colossal Earh landscapes, or sand seas, with towering dunes migrating across endless plains. Interspersed with these dunes would be vast salt flats and playas, the ghostly remnants of ancient, ephemeral lakes that would occasionally fill with rainwater only to evaporate under the relentless sun, leaving behind thick crusts of minerals. The air would have been perpetually dusty, often tinged red by the oxidized iron minerals that thrived in such dry, oxygen-rich environments. Evidence for this extreme aridity comes from the geological record itself. Extensive deposits of evaporate minerals like halite, rock salt, and gypsum, typically formed when large bodies of water evaporate in arid conditions, are found across continents that were once part of Pangea's interior. Equally telling are the ubiquitous red beds, massive sequences of reddish sandstones and shales. The distinctive red color is a telltale sign of iron minerals oxidized by exposure to air and minimal water, indicating long periods of intense dryness and hot conditions. Furthermore, fossil evidence from these regions supports the notion of a parched landscape, with plant species adapted to extreme drought conditions, such as early conifers and cycads with waxy cuticles and deep root systems, and animal assemblages that could survive in such challenging environments. The sheer size of Pangea amplified this effect. There was simply nowhere for the moisture to come from for the central parts, creating a climate system largely independent of oceanic influence. In stark contrast to the parched interior, Pangea's coastal regions offered a very different picture, a testament to the moderating influence of the vast Panthalassic Ocean that surrounded the supercontinent, and the Tethys Ocean, which was a significant embayment along its eastern flank. These coastal areas, stretching along the edges of what would become North America, Europe, Asia, Australia, and parts of Gondwana, experienced climates far more akin to what we might recognize today. Here, proximity to the ocean meant higher humidity, more consistent rainfall, and significantly less extreme temperature fluctuations between day and night and across seasons. The air, carrying evaporated moisture from the ocean, would deposit its bounty upon these landmasses, allowing for the development of lush ecosystems. Evidence for these more temperate and humid coastal environments is abundant. Vast coal deposits, a significant portion of the world's coal reserves, were laid down during the Carboniferous and Permian periods, precisely when Pangea was assembling and reaching its peak. These coal seams are the fossilized remains of ancient swamps and forests, indicating areas of abundant vegetation and consistently high rainfall, particularly in the equatorial and subequatorial regions. Think of the enormous rainforests of the Carboniferous, teeming with giant lycopods, ferns, and horsetails, which would later form the basis of our modern energy supply. Furthermore, the presence of diverse marine fossil beds along ancient coastlines, indicating thriving reef systems and shallow marine life, also points to stable, moderate conditions. Ocean currents, though their exact patterns within the immense Panthalassic Ocean are still a subject of active research, would have played a crucial role in distributing heat and moisture along Pangea's extensive coastlines, further moderating the climate and supporting rich biodiversity compared to the arid interior. One of the most fascinating climatic phenomena, driven by Pangea's immense size, was the supercontinental monsoon system. Monsoons, as we know them today, are seasonal reversals in wind direction caused by differential heating and cooling of land and ocean. On Pangea, this effect was amplified to an extraordinary degree. The vast landmass would heat up much faster and to higher temperatures than the surrounding Panthalassic Ocean during the summer months. This intense heating would create a massive low-pressure system over the interior of the supercontinent. Simultaneously, the cooler ocean would maintain a relatively higher pressure. This dramatic pressure gradient would draw vast quantities of moist air from the ocean towards the continental interior. The result was a colossal summer monsoon, delivering torrential rainfall, particularly to the coastal and near-coastal regions, and even penetrating some distance inland. This seasonal deluge would have transformed vast river systems, caused widespread flooding, and supported significant vegetation in otherwise dry regions. During the winter months, the situation would reverse. The vast landmass would cool down significantly more rapidly and to lower temperatures than the ocean, creating a huge high-pressure system over the continent. This would force dry, cold air outwards towards the ocean, resulting in a severe winter dry season for much of Pangea. The impact of these monsoons on the landscape was profound. The seasonal deluges would have sculpted the land, creating distinctive sedimentary structures known as rhythmites, alternating layers of coarse and fine sediment, indicative of seasonal deposition. Ancient soil formations, or paleosols, found in the geological record also show characteristics of environments subjected to marked wet and dry cycles. Furthermore, fossil plant communities discovered in these regions exhibit adaptations to cope with these extreme seasonal variations, thriving during the wet season and enduring the prolonged dry periods. The sheer scale of Pangea meant that this monsoon system was a global climatic engine, far more powerful and extensive than any monsoonal system we see today, influencing climate patterns across vast swathes of the supercontinent. Even within the context of a supercontinent, Earth's dynamic climate system was still subject to periods of profound global cooling, and Pangea's formation itself was intimately linked with a major ice age, the Permo-Carboniferous glaciation. This was not merely a localized cold snap, but a truly global event, with ice sheets covering enormous portions of what would eventually become the southern continents of Gondwana, Africa, South America, Antarctica, Australia, and India. The primary cause of this glaciation was a combination of factors, including the unique configuration of landmasses. As the continents began to coalesce into Pangea, a significant portion of Gondwana drifted directly over the South Pole. This polar positioning provided the ideal conditions for the accumulation of vast ice sheets, as snowfall persisted year-round and did not melt sufficiently in the warmer months. Other contributing factors included significant changes in atmospheric carbon dioxide levels, likely due to the massive burial of organic carbon that formed the coal deposits of the Carboniferous period, which removed CO2 from the atmosphere and led to a global cooling trend. Changes in ocean circulation patterns, as the continents moved and landlocked major seaways, also played a role in altering heat distribution across the planet, favoring the growth of ice. The evidence for this massive glaciation is irrefutable and widespread. Geologists have discovered extensive tillites, distinctive sedimentary rocks formed from the debris deposited by glaciers, across all the former Gondwanan continents. These tillites are often found in association with striated pavements, bedrock surfaces that bear unmistakable scratch marks and grooves etched by the grinding movement of colossal ice sheets. Additionally, the presence of U-shaped valleys formed by glacial erosion and dropstones, large boulders deposited far from their source by melting icebergs, further corroborate the existence of these ancient glaciers. As Pangea fully assembled and slowly began its northward drift over millions of years, these massive ice sheets gradually retreated, marking the transition out of this prolonged glacial epoch and into the generally warmer conditions of the Triassic and Jurassic periods that followed. The fact that a major ice age could occur even as continents were coalescing highlights the complex interplay of plate tectonics, atmospheric chemistry, and orbital dynamics in shaping Earth's long-term climate. Beyond localized climate zones, Pangea's immense landmass profoundly altered global circulation patterns, both in the atmosphere and in the oceans. The oceanic realm surrounding Pangea was dominated by the vast Panthallassic Ocean, an unbroken expanse of water that would have acted as a truly global ocean. Without the numerous continental barriers that fragment today's oceans into separate basins, the Panthallassa would have allowed for unimpeded, vast ocean currents to flow across its entire extent. This could have led to a less complex but potentially more uniform deep water circulation in certain regions, and the absence of major land masses at equatorial latitudes would have allowed for a massive circumequatorial current to girdle the globe, potentially distributing heat more evenly around the equator. However, the Tethys Ocean, a large wedge-shaped embayment on Pangea's eastern side, was also a critical player. As a relatively shallow, warm seaway, it would have acted as a massive heat reservoir, influencing temperatures and salinity across its vast basin and exchanging water with the Panthalassa. The interaction of these two enormous water bodies would have created unique current systems, unlike anything we observe today. Atmospheric circulation on Pangea also operated on a different scale. While the fundamental principles of atmospheric cells, the Hadley, Ferrel, and polar cells, would still have been in operation, their extent and intensity would have been greatly modified by the supercontinent's presence. The immense landmass acted as a giant thermal engine, creating enormously powerful seasonal high and low-pressure systems that drove the supercontinental monsoons. The absence of major mountain ranges in certain areas, which largely formed after Pangea broke up due to subsequent continental collisions, would have meant fewer topographic barriers to airflow, potentially allowing for more consistent, broader wind patterns. Furthermore, the sheer scale of Pangea meant that climatic events in one region could have had far-reaching teleconnections, interconnected atmospheric and oceanic systems that allowed for climatic signals to be transmitted across vast distances. For example, changes in monsoon intensity over one part of the supercontinent could have altered rainfall patterns thousands of miles away. The vastness of the Panthallassic Ocean also meant that the atmospheric moisture supply for the coastal regions was virtually limitless, contributing to the dramatic contrast with the arid interior. Ultimately, Pangea's unique climate signature, characterized by its vast arid heart, its more temperate and humid coastlines, its powerful monsoonal breathing, and its interlude with a major ice age, had a profound impact on life and evolution. The extreme conditions of the interior would have acted as a powerful selective pressure, driving the evolution of drought-resistant plants and animals adapted to scarcity. The lush coastal and monsoonal regions, on the other hand, would have supported greater biodiversity and served as cradles for the evolution of new forms of life. The supercontinent's configuration also meant that species could disperse across enormous land masses, leading to relatively less provinciality, regional uniqueness in terrestrial faunas and floras compared to today's separated continents. Understanding Pangea's climate is not just an academic exercise. It provides invaluable insights into the dynamic nature of Earth systems and how the planet's physical architecture dictates its climate, shaping the very course of life's history. The lessons learned from Pangea underscore the profound influence of continental configuration on atmospheric and oceanic dynamics, reminding us that our planet's climate is a constantly evolving interplay of geological, atmospheric, and biological forces. It truly was a world of climatic extremes, a testament to the power of a single, colossal landmass to reshape Earth's entire environmental blueprint for hundreds of millions of years. The story of Pangea is not just about its majestic assembly and its reign as a unified supercontinent. It is also, inevitably, about its dramatic demise. Like all supercontinents before it, Pangea was destined to break apart, yielding to the relentless forces of plate tectonics that constantly reshape our planet's surface. This colossal breakup was not a sudden, cataclysmic event, but a protracted process spanning tens of millions of years, beginning in the late Triassic period and continuing well into the Jurassic. The first signs of this impending fragmentation were subtle at first. A whisper of tension in the crust, followed by broad uplift, then the fracturing of the lithosphere, leading to the formation of massive rift valleys. Understanding how Pangea began to break apart is crucial to comprehending the current configuration of our continents and oceans, as the scars of this ancient breakup are still visible in the geological record, providing an invaluable window into the dynamic forces that tear continents asunder. Why do supercontinents, once formed, eventually succumb to fragmentation? This question lies at the heart of plate tectonics. While the Earth's interior is a swirling cauldron of convection currents, the mechanisms that initiate continental rifting are complex and multifaceted. One of the leading theories points to the supercontinent insulator effect. Imagine Pangea, a vast blanket of thick continental lithosphere, effectively acting as an insulating layer, trapping heat beneath it from the Earth's mantle. This accumulated heat, generated by the slow decay of radioactive elements deep within the Earth, causes the mantle directly beneath the supercontinent to become hotter and more buoyant. As this superheated mantle rises, it pushes upwards on the overlying crust, causing it to dome and stretch. This upward doming creates immense tensional stresses within the rigid continental crust. Think of trying to stretch a piece of taffy. Eventually, it thins and breaks. The crust responds to these stresses by developing fractures and faults. Adding to this internal heat buildup, the role of mantle plumes and hotspots is also considered crucial. A mantle plume is a column of hot, buoyant rock rising from deep within the Earth's mantle, potentially originating from the core mantle boundary. When such a plume reaches the base of the lithosphere, it can create a localized hotspot of intense heat and magmatic activity. The immense heat from these plumes further weakens the overlying crust, making it more susceptible to fracturing. The buoyancy of the rising plume also contributes to the uplift of the continental crust, further exacerbating the tensional forces. A prime example of such a massive magmatic event associated with the early breakup of Pangea is the Central Atlantic Magmatic Province, CAMP. This colossal outpouring of basaltic lavas and intrusive igneous rocks occurred around 200 million years ago, right at the onset of the Atlantic Ocean's opening. CAMP is one of the largest igneous provinces in Earth's history, covering an area of several million square kilometers across 4 continents: North America, South America, Africa, and Europe. Its sheer scale points to a massive thermal event, likely driven by one or more mantle plumes, which significantly softened and fractured the lithosphere, paving the way for continental separation. While slab pull, the force exerted by a subducting oceanic plate as it sinks into the mantle, and ridge push, the force exerted by new oceanic crust forming at mid-ocean ridges, are dominant forces in present-day plate tectonics during the initial rifting phase. It is the internal heating and buoyancy from the mantle that are thought to be the primary drivers, effectively pulling the continents apart from within, or perhaps more accurately, pushing them apart. The first signs of continental rifting were not dramatic, oceanic-scale chasms, but rather more subtle manifestations of crustal tension. The process typically began with broad, regional uplift and doming of the crust. This upwarping, driven by the buoyant forces of the hot, rising mantle beneath, would have created elevated plateaus across the supercontinent. As the crust continued to stretch and thin due to these underlying forces, it would begin to fracture. These fractures developed into systems of normal faults, where blocks of crust slide downwards relative to each other along inclined planes. The result of this faulting is the formation of characteristic geological structures known as grabens and horsts. Grabens are the down-dropped blocks of crust, creating elongated valleys or basins, while horsts are the uplifted blocks on either side. These grabens are the embryonic rift valleys, the very first fissures in the supercontinent's armor. Imagine stretching a piece of clay. It will thin in the middle and eventually crack, with segments dropping down. This is precisely what happens on a grand geological scale. Concurrent with the faulting, and often driven by the same underlying magmatic activity, was extensive volcanism. As the continental crust thinned, the pressure on the underlying mantle was reduced, leading to decompression, melting. This melting generates vast quantities of magma, primarily basaltic in composition, which rises to the surface through the newly formed faults and fissures. The result was enormous eruptions of flood basalts, covering vast areas in successive layers of lava. The previously mentioned Central Atlantic Magmatic Province, CAMP, is a prime example of such flood basalt volcanism, laying down millions of cubic kilometers of lava. These massive volcanic events not only provide direct evidence of magma generation during rifting, but also contribute to the weakening and eventual rupture of the continental lithosphere. The sheer volume of these eruptions indicates an immense amount of heat transfer from the mantle, a signature of a truly profound geological event. The major rift systems of Pangea represent the birthplaces of our modern oceans. The most prominent and well-studied of these is the Central Atlantic Rift System. This rift initiated between what would eventually become North America and Africa, and later propagated southwards to separate South America from Africa, forming the South Atlantic Rift System. The process began not as a single, continuous tear, but as a series of disconnected rift basins, often several hundred miles long, which gradually linked up over tens of millions of years. These early rift basins, such as the Newark supergroup basins along the eastern seaboard of North America, were sites of intense sedimentation and volcanism. They collected enormous volumes of fluvial, river, and lacustrine, lake sediments, interbedded with basaltic lava flows and volcanic ash layers. The South Atlantic Rift followed a similar pattern, albeit a bit later, progressively unzipping the continents from north to south. To visualize this ancient process, geologists often look to modern analogues like the East African Rift System. This active rift provides a living laboratory for studying continental breakup, displaying all the hallmarks of incipient rifting: broad uplift, numerous normal faults forming characteristic graben and horst topography, a chain of volcanoes, some highly active, and elongated lakes filling the down-dropped basins. While the East African Rift is still in its early stages, it illustrates the very processes that tore Pangea apart. It's important to note that not all rifts succeed in becoming new ocean basins. Many initial rift arms fail to propagate and become what are known as failed rifts or aulocogens. These are ancient, aborted rift valleys that become zones of weakness within the continental crust. They often accumulate thick sequences of sediments and can sometimes be reactivated by later tectonic forces. Examples include the Benue Trough in West Africa, which was a failed arm of the South Atlantic Rift, and the Reelfoot Rift in the central United States, which is part of a failed rift system associated with the early opening of the Iapetus Ocean long before Pangea. These failed rifts provide valuable geological archives, preserving thick sedimentary records of their formation and evolution, often containing resources like oil and gas. The evidence for Pangea's breakup and the rifting process itself is abundant and diverse, gleaned from various branches of geological science. One of the most compelling lines of evidence comes from the rock formations found within these ancient rift valleys. As the grabens formed, they created depressions that collected vast amounts of sediment. These sedimentary sequences are often characterized by fluvial and lacustrine deposits, sandstones, shales, and conglomerates laid down by rivers and in lakes that filled the basins. The presence of red beds, mentioned earlier in the context of arid interiors, is also common in rift environments, as the exposed, oxidized iron minerals reflect the hot, often arid conditions prevalent in these nascent rift valleys. In more restricted basins, particularly in early stages where ocean waters periodically invaded and then retreated, thick evaporite deposits like halite, rock salt, and gypsum are found, indicative of repeated cycles of inundation and evaporation. These salt layers are particularly important for oil and gas exploration. In some more humid rift segments, or during specific climatic periods, lush vegetation in swampy environments could lead to the formation of coal seams, providing further insight into the local conditions within the rift. Igneous rocks provide perhaps the most dramatic evidence of rifting. The immense volumes of flood basalts, such as those from the Central Atlantic Magmatic Province, the Paraná-Etendeka Province, South America, Africa, and the Karoo Province, Southern Africa, are direct indicators of massive magma generation as the continental crust thinned and stretched. These basaltic flows often exhibit characteristic columnar jointing, where the lava contracts and cracks into hexagonal columns as it cools, and their vast aerial extent speaks volumes about the scale of the magmatic activity. Beyond surface flows, the intrusion of magma into cracks and layers within the crust formed extensive networks of dikes, vertical intrusions, and sills, horizontal intrusions. These fossilized magma conduits are essentially the plumbing system of the rifting process. Geochemical analysis of these igneous rocks also provides crucial information about the source of the magma, often indicating melting of the underlying mantle and distinctive compositions related to extensional tectonics. Structurally, the presence of widespread normal faults is the definitive proof of crustal extension. These faults are often identified through detailed geological mapping on the surface, or more powerfully, through seismic imaging techniques, which allow geologists to see beneath the Earth's surface and identify fault geometries. The characteristic graben and horst structures, sometimes still preserved as topographic features, also bear witness to the immense tensional forces. Geophysical studies, such as seismic reflection surveys and gravity anomaly mapping, can reveal areas where the continental crust has been significantly thinned by rifting, even if these ancient rifts are now buried under kilometers of younger sediments. The crustal thinning is a direct consequence of the stretching that precedes breakup. Paleomagnetism also plays a vital role. By studying the magnetic orientation of volcanic rocks and sediments within rift zones, scientists can determine the age of the rifting events and track the progressive widening of the rift over geological time. As new oceanic crust is generated at mid-ocean ridges, the next stage after rifting, it records the Earth's magnetic field at the time of its formation, creating a symmetrical pattern of magnetic stripes that allows for the precise dating of seafloor spreading and, by extension, the timing of continental separation. Finally, though not direct evidence of rifting itself, the distribution of land-dwelling fossils provides powerful indirect evidence for continental breakup. The striking similarities in fossil flora and fauna found on continents now separated by vast oceans, for instance, the presence of the ancient reptile Lystrosaurus on Africa, Antarctica, and India, demonstrate that these land masses were once connected as part of Pangea. The subsequent divergence of species after the breakup then provides a biological clock for the timing of continental separation along these very rift lines. The culmination of the rifting process occurs when the continental crust completely ruptures, allowing magma to rise directly from the mantle to form new oceanic crust. This marks the transition from a continental rift valley to a nascent ocean basin with active seafloor spreading. The Red Sea, a narrow, linear body of water separating Africa from the Arabian Peninsula, is a prime modern example of this intermediate stage, where continental rifting is giving way to the formation of a new ocean basin. It vividly illustrates the processes that began Pangea's dismantling. In conclusion, the breakup of Pangea was a monumental geological event, driven by complex forces within the Earth's mantle. The first signs of this fragmentation were not the dramatic separation we see today, but rather a protracted process of crustal tension, uplift, faulting, and massive volcanism, leading to the formation of vast rift valleys. The geological record, from the sedimentary sequences in ancient rift basins to the colossal flood basalts that mark sites of intense magmatism and the ubiquitous normal faults that characterize extensional tectonics, provides overwhelming evidence of this extraordinary chapter in Earth's history. These scars of Pangea's birth are still visible and continue to inform our understanding of plate tectonics, reminding us that our seemingly stable continents are in a perpetual state of slow, majestic motion, cyclically assembling into supercontinents and then tearing themselves apart again, only to begin the long, slow journey of reassembly anew. Imagine our planet as a giant, living entity, constantly in motion, churning and breathing with an internal fire that shapes its very surface. For eons, the continents have danced across this surface, coming together in monumental unions like Pangea, and then, just as dramatically, tearing themselves apart. But what power could be so immense, so fundamental, that it could orchestrate such a grand geological ballet? The answer, many geoscientists believe, lies deep within the Earth, in phenomena known as mantle plumes and hotspots. These aren't just some minor geological curiosities. They are, in essence, the planet's internal furnaces, delivering heat from below and providing crucial signals that betray the slow, deliberate, yet ultimately irresistible forces of tectonic change. To truly grasp the role of mantle plumes and hotspots, we need to take a journey to the Earth's fiery heart. Forget everything you thought you knew about quiet, stable ground. Beneath our feet is a dynamic, convective system. The mantle, the vast layer between the Earth's crust and its molten outer core, is not solid in the way we understand rock on the surface. Instead, over geological timescales, it behaves like a thick, incredibly viscous fluid, slowly flowing and circulating in a process called convection. Think of it like a pot of incredibly thick stew simmering on a stove. As the heat rises from the bottom, the stew itself begins to move with hotter, less dense material, rising, cooling, and then sinking again. In the Earth's mantle, this process happens on scales of millions of years, but the principle is the same. Mantle plumes are essentially gigantic upwellings of abnormally hot rock that originate from deep within this mantle. Many scientists believe they rise from the very boundary between the Earth's core and mantle, an enigmatic region that's often called the D double prime layer. Here, at depths of nearly 3,000 kilometers, temperatures are staggeringly high, approaching those at the surface of the Sun. As the core mantle boundary heats the lowermost mantle, some of this material becomes buoyant and begins to rise. It's a bit like a hot air balloon. As the air inside heats up, it becomes less dense than the surrounding air and ascends. Similarly, these superheated blobs of mantle material, slightly less dense than the cooler mantle around them, begin a slow, arduous journey upwards. This ascent is not a chaotic scramble. It's a remarkably organized process, often forming a mushroom-shaped structure. The plume typically has a narrow, conduit-like tail that extends all the way down to its source at the core mantle boundary, acting as a channel for the rising hot material. At the top, closer to the Earth's surface, this rising material spreads out, forming a much wider, more voluminous plume head. It's this plume head, typically hundreds to over 1,000 kilometers across, that does the heavy lifting when it comes to impacting the Earth's lithosphere. That rigid outer layer composed of the crust and uppermost mantle, the very layer that forms our continents and ocean floors. When a mantle plume head encounters the base of the lithosphere, which is much cooler and more rigid, the effect is profound. First, the sheer volume of hot, buoyant material beneath the lithosphere causes it to dome upwards. Imagine pushing up on a carpet from underneath. It creates a bulge. This uplift can be significant, sometimes hundreds of meters to over a kilometer, creating broad, elevated regions on the Earth's surface. This doming stretches the lithosphere, placing it under tension. Think of stretching a piece of rubber. It becomes thinner in the middle. As the lithosphere stretches, it begins to fracture, forming a series of parallel cracks or faults. These faults often delineate rift valleys, which are essentially long, narrow depressions where the Earth's crust is pulling apart. But the plume's influence doesn't stop at mere stretching. The intense heat transferred from the plume head to the base of the lithosphere has an even more dramatic effect. It melts the overlying mantle rock, creating vast quantities of magma. This magma, being less dense than the surrounding solid rock, rises through the fractures and faults in the stretched lithosphere, erupting onto the surface as colossal volcanic events. These events are far beyond anything we typically witness today. We're talking about what geologists call large igneous provinces, or LIPs. These are enormous outpourings of lava, often basaltic in composition, that can cover areas the size of entire countries and involve volumes of magma reaching hundreds of thousands to even millions of cubic kilometers. The Deccan Traps in India or the Siberian Traps in Russia are two well-known examples of such ancient ellipses, providing tangible evidence of past plume activity. This brings us directly to the idea of heat from below driving apart the continents. It's not just a poetic phrase, it's a description of a fundamental process. The sustained heat and material flux from a powerful mantle plume can weaken the continental lithosphere to such an extent that it eventually breaks apart. The uplift creates slopes that allow gravity to exert a pulling force, and the thinning of the lithosphere makes it more susceptible to the tensional stresses. The massive volumes of magma erupted further contribute to the weakening and buoyancy of the crust. Once rifting begins, it can sometimes evolve into a full-blown spreading center where new oceanic crust is generated and continents move further and further apart. The process is akin to a continent being slowly cooked and pulled apart from beneath. A classic example of this process, often cited in the context of continental breakup, is the theory that the initial rifting of the supercontinent Pangea was instigated, or at least significantly influenced, by one or more massive mantle plumes. Imagine Pangea as a vast, unified landmass subjected to immense internal stresses. When a powerful plume head ascended beneath its central part, it would have caused broad uplift and massive volcanic eruptions. The prodigious volumes of basaltic lavas that erupted would have formed a huge volcanic plateau, effectively preconditioning the continental lithosphere for eventual rupture. This internal weakening, combined with the ongoing forces of plate tectonics, could then initiate the continental breakup. Hotspots are the surface expressions of these mantle plumes. When a plume rises and melts the overlying lithosphere, it creates a persistent source of volcanism. The key characteristic of many hotspots, like the one beneath Hawaii, is that they tend to remain relatively stationary in the mantle, even as the lithospheric plate moves over them. This stationary nature creates a trail of volcanoes on the moving plate, a chain of islands or seamounts, with the youngest and most volcanically active volcanoes located directly over the hotspot. Think of a conveyor belt moving over a fixed heat lamp. The lamp burns a continuous line on the belt. This hotspot track provides invaluable evidence for plate motion and, crucially, suggests the deep-seated origin of mantle plumes, distinct from the shallower processes that occur at plate boundaries. So, how does volcanic activity signal tectonic changes? The answer lies in the scale, type, and location of the eruptions. When we see the sudden, voluminous eruption of flood basalts, the type of volcanism associated with ellipse, over a relatively short geological period, a few million years, which is lightning fast in geological terms, and spanning vast areas, it's a strong signal that something profound is happening beneath the surface. These are not your typical cone volcanoes found at subduction zones, or even the effusive eruptions at mid-ocean ridges. Flood basalts indicate an extraordinary influx of heat and magma from the mantle, far beyond what normal plate boundary processes can account for. Moreover, the composition of these flood basalts provides another clue. They are often tholeiitic basalts, which are characteristic of magmas derived from the deep melting of the mantle. This geochemical signature helps geologists differentiate plume-related volcanism from volcanism associated with shallower processes, such as the stretching of continental crust alone, which tends to produce more silicic lavas. Furthermore, the location of this massive volcanism is critical. If it occurs in the interior of a continent, far from existing plate boundaries, it screams mantle plume. Conventional wisdom dictates that most volcanism occurs at plate boundaries, where plates diverge, converge, or slide past each other. So, when you find evidence of extensive, voluminous volcanism in the middle of a continental plate, it's a strong indicator that a hot, buoyant mantle plume has ascended from deep within the Earth, pushing against the base of the lithosphere and causing it to rupture. The earliest stages of Pangea's breakup, for instance, are marked by precisely this kind of intracontinental flood basalt volcanism, spread across vast regions that would later become parts of North America, South America, Africa, and Europe. This was the Earth's way of telling us that the supercontinent was beginning to strain under immense internal pressure. The sequence of events typically goes like this. First, the lithosphere bows upwards due to the rising plume head. This causes stretching and the formation of rift valleys. Then, as the heat increases and the lithosphere thins, massive volumes of magma are generated and erupt onto the surface as flood basalts. This period of intense volcanism effectively marks the point of no return for the continent. The crust is irrevocably weakened and begins to separate. The eruption of these flood basalts often precedes the actual onset of seafloor spreading by a relatively short geological time. They are the dramatic overture to the grand symphony of continental breakup, a fiery pronouncement that a new ocean basin is about to be born. Consider the Central Atlantic Magmatic Province, or CAMP, which we'll delve into more deeply in the next section. This enormous outpouring of magma, which occurred around 200 million years ago, wasn't just a random volcanic event. It was strategically located along the suture lines where Pangea was poised to rupture. Its sheer scale and timing provide compelling evidence that it was intimately linked to the forces that initiated the opening of the Atlantic Ocean. The volcanic activity was a direct signal, a geological siren, announcing the tectonic changes that would redefine the Earth's geography for millions of years to come. Beyond the initial rifting, mantle plumes and hotspots continue to play a role in the ongoing evolution of the Earth's surface. As plates move over stationary hotspots, they create those iconic chains of volcanic islands, like the Hawaiian Emperor Seamount Chain. These tracks are not just pretty pictures. They provide invaluable data for understanding the direction and speed of plate motion over geological time. They are, in a way, continuous signals from the deep mantle, marking the path of the continents as they drift across the globe. In conclusion, the story of mantle plumes and hotspots is one of deep Earth dynamics, profoundly influencing surface tectonics. They are the conduits through which immense heat and material from the planet's interior are delivered to its rigid outer shell. This heat from below acts as a powerful engine, causing uplift, stretching, and ultimately the catastrophic rupture of continental lithosphere. The resulting voluminous volcanic activity, particularly the formation of large igneous provinces, serves as an undeniable signal of these profound tectonic shifts. These fiery outpourings are not just geological footnotes, they are the Earth's way of communicating its inner turmoil, telling us when a supercontinent like Pangea is under immense stress and is about to embark on a new, dramatic chapter of its journey across the face of our ever-changing planet. They are the drivers, the architects, and the heralds of the planet's grandest geological transformations. Imagine Pangea, the legendary supercontinent, a vast, monolithic landmass that dominated the Earth's surface for hundreds of millions of years. It was an immense continent, a single, sprawling tapestry of land stretching from pole to pole, where ancient deserts baked under harsh suns and towering mountain ranges, long since eroded, stood as testaments to the titanic collisions that had formed it. For a significant portion of Earth's history, life, both on land and in the oceans, experienced an Earth where continental drift, at least in the sense of separate land masses moving apart, was largely paused. But even the mightiest structures eventually succumbed to internal stresses, and Pangea was no exception. Its breakup, a geological event of unprecedented scale, didn't happen overnight. It was a protracted, tumultuous process, and its first, most dramatic chapter was the birth of the Atlantic Ocean, heralded by an extraordinary geological phenomenon, the Central Atlantic Magmatic Province, or CAMP. Before we delve into the fiery birth of the Atlantic, let's set the stage for Pangea itself. Assembled through a series of continental collisions over a span of millions of years, culminating around 300 million years ago, Pangea was a truly colossal continent. Its existence profoundly influenced global climate, ocean circulation, and the evolution of life. But beneath its immense weight and spanning its vast expanse, the forces of plate tectonics were silently at work. Heat from the Earth's interior was continually driving convection currents in the mantle, causing immense stresses to build up within the continental lithosphere. Just like a sheet of ice cracking under pressure, Pangea, despite its apparent stability, was experiencing increasing tension. The first whispers of Pangea's demise began not with a bang, but with a slow, almost imperceptible stretching. This initial phase, known as continental rifting, involved the lithosphere slowly pulling apart. Imagine trying to stretch a thick piece of dough. It thins in the middle and eventually tears. Similarly, as the forces pulling Pangea apart intensified, the continental crust began to stretch and thin. This process created a series of interconnected rift valleys, grabens, down-dropped blocks of crust between faults, and half-grabens, forming a complex network of basins that would later become the embryonic Atlantic Ocean. Rivers flowed into these developing basins, depositing sediments that would eventually be buried and preserved as a geological record of this tumultuous period. However, the truly spectacular act in this geological drama, the one that unequivocally signaled the beginning of Pangea's fragmentation, was the eruption of the Central Atlantic Magmatic Province, or CAMP. This wasn't just a localized volcanic event. It was an eruption of truly staggering proportions, an outpouring of lava on a scale almost unimaginable today. Occurring roughly 200 million years ago, at the boundary between the Triassic and Jurassic periods, CAMP represents one of the largest igneous provinces on Earth. Its immense scale and its precise timing with the onset of Atlantic rifting leave little doubt that it was a pivotal player in Pangea's undoing. Consider the sheer scope of CAMP. Its lavas are found across 4 continents: northwestern Africa, southwestern Europe, North America, and South America, regions that were once conjoined within Pangea. The total volume of erupted magma is estimated to be somewhere between 2 and 4 million cubic kilometers, an amount that could bury entire nations under hundreds of meters of solid basalt. To put that into perspective, imagine the largest volcanic eruption in recorded human history, like the eruption of Mount Tambora in 1815, and multiply its output by many, many thousands. That's the scale we are talking about. These were not explosive conical volcanoes, but rather vast, effusive eruptions that poured out immense sheets of basaltic lava, creating extensive flood basalts. The characteristics of the CAMP basalts themselves tell a compelling story. They are predominantly tholeiitic basalts, a type of lava that originates from the partial melting of the Earth's mantle. This geochemical signature is crucial because it indicates a deep-seated source for the magma, rather than simply shallow melting of the crust. The rapid and voluminous nature of these eruptions, occurring over a geologically short time frame of perhaps 1 to 5 million years, strongly suggests the involvement of a mantle plume head. As we discussed in the previous section, when a massive plume head rises from the deep mantle and impinges upon the base of the continental lithosphere, it causes immense melting and uplift, leading to these catastrophic outpourings of magma. The CAMP eruptions are widely interpreted as the surface expression of such a colossal mantle plume that ascended directly beneath the nascent rift zone of Pangea. The timing of CAMP is perhaps its most significant feature. The vast majority of the eruptions occurred within a span of just a few million years, precisely when geological evidence indicates the initial breakup of Pangea began and the very first stages of the Atlantic Ocean started to form. This near-perfect chronological correlation is not coincidental. It strongly suggests a causal link. The massive injection of heat and magma from the CAMP plume would have further weakened the already stretched and thinning continental lithosphere, effectively providing the final push that led to the rupture and the onset of seafloor spreading. It's like the Earth itself was experiencing a catastrophic internal hemorrhage, a fiery release of pressure that signaled a fundamental shift in its tectonic regime. The concept of a proto-ocean is key to understanding the early Atlantic. A proto-ocean is not a fully fledged, wide ocean basin like the Atlantic we see today. Instead, it's a narrow, embryonic ocean, characterized by young, newly formed oceanic crust. In the early stages of rifting, as the continental crust finally tears apart, the underlying mantle begins to upwell and melt, forming new oceanic crust at a nascent spreading center. This process is called seafloor spreading. The Proto-Atlantic would have been a relatively shallow basin, perhaps resembling the modern Red Sea, with high heat flow and significant volcanic activity along its central axis. The Atlantic's birth was not a single, instantaneous event, but a progressive opening that started in the central region and then propagated northward and southward. The initial break, marked by the camp volcanism, occurred between what would become North America and Africa, South America. As seafloor spreading continued, the rift widened, and new oceanic crust was continuously generated along the mid-Atlantic ridge, the colossal underwater mountain range that now runs down the center of the Atlantic. Evidence for this early Atlantic seafloor spreading comes from a variety of sources. Magnetic anomalies, preserved in the newly formed oceanic crust, act like a geological barcode, recording reversals in Earth's magnetic field. These symmetrical patterns on either side of the mid-Atlantic ridge provide unequivocal proof of seafloor spreading and allow geologists to reconstruct the history of ocean basin widening. Additionally, the presence of rift valleys and nascent ocean crust in the earliest parts of the Atlantic, as well as the distribution of marine sediments that transitioned from shallow water to deep water faces, all paint a consistent picture of a continent slowly tearing apart and a new ocean being born. The environmental consequences of the camp eruptions were immense and far-reaching. The release of such vast quantities of volcanic gases, including carbon dioxide and sulfur dioxide, into the atmosphere would have caused profound climate change. Massive injections of carbon dioxide could have led to significant global warming and ocean acidification, disrupting marine ecosystems. Sulfur dioxide and aerosols would have caused short-term cooling events, followed by longer-term warming. Many scientists propose a strong link between the camp eruptions and the Triassic-Jurassic extinction event, one of the Earth's Big Five mass extinctions. While the exact mechanisms are still debated, it is plausible that the massive environmental upheaval caused by this volcanic catastrophe pushed many species beyond their limits, leading to a widespread loss of biodiversity. This highlights that the breakup of Pangea and the formation of the Atlantic was not merely a geological rearrangement, it was an ecological reset. As the Proto-Atlantic widened, it began to exert its own influence on global systems. The formation of a new ocean basin fundamentally altered ocean currents, breaking up the single, vast global ocean that had surrounded Pangea. This would have redistributed heat around the planet, influencing global climate patterns. New coastal environments were created, providing opportunities for the diversification of marine life. As the continents drifted further apart, they began to develop their own distinct biotas, leading to the evolutionary divergence of species that had once shared the same supercontinental landmass. The story of the Atlantic is far from over. The mid-Atlantic ridge continues to be an active spreading center, generating new oceanic crust and slowly widening the basin by a few centimeters each year. The continents that once formed Pangea, North America, South America, Europe, and Africa, continue their inexorable drift away from each other, a testament to the enduring power of plate tectonics. The grand geological ballet initiated by the breakup of Pangea, triggered and marked by the colossal eruptions of the Central Atlantic magmatic province, continues to unfold, shaping the world we live on today. In essence, the early Atlantic was more than just a body of water appearing on a map. It was the physical manifestation of Pangea's colossal unraveling. The Central Atlantic magmatic province was not merely a footnote in this story. It was the opening declaration, a fiery, undeniable signal from the Earth's interior that a supercontinent was fracturing and a new ocean was destined to be born. It underscores the profound interconnectedness of deep Earth processes, surface volcanism, and the grand narrative of continental drift, a story continuously written over hundreds of millions of years on the ever-evolving canvas of our planet. The proto-ocean was a dramatic, often violent, proving ground for the forces that would ultimately sculpt the familiar continental configuration of today, a dynamic and enduring legacy of Pangea's final act. Before the grand unraveling of Pangea began in earnest, in the deep stretches of the Triassic period, the supercontinent presented a remarkably uniform terrestrial environment. Picture a single, immense landmass stretching from pole to pole, characterized by a largely continental climate. The interiors would have been arid, experiencing extreme seasonal temperature swings, while coastal regions, though still vast, would have offered more humid and temperate conditions. This homogeneity meant that species, whether they were lumbering cynodonts, early dinosaurs, or the resilient plant life of the time, could potentially disperse across enormous distances. There were no vast oceans acting as insurmountable barriers to gene flow. Genetic material could mix relatively freely across the vast continental expanse. This led to a situation where, for many widespread groups, there was less regional variation than we see today. The world was, in a sense, a much smaller, more interconnected place for land-dwelling organisms, fostering a degree of biological uniformity across what would one day become widely separated continents. However, beneath this seemingly stable facade, the Earth's powerful internal engines were already stirring. Driven by the slow but relentless convection currents within the planet's mantle, Pangea began to stretch, groan, and fracture. This wasn't an instantaneous cataclysm, but a protracted geological process spanning tens of millions of years. The earliest signs of this breakup were the formation of vast rift valleys, akin to the East African rift system we observe today, but on a much grander scale. These nascent cracks in the continental crust were areas of intense geological activity, characterized by extensive volcanism. Magma, rising from the Earth's interior, would spill out onto the surface, creating enormous flood basalt provinces that fundamentally altered local landscapes and atmospheric composition. These early rifts, while not yet open oceans, would have already begun to create physical barriers, even if subtle, to the movement of some species. Mountains might have been uplifted along the rift margins, and valleys might have become increasingly deep and difficult to traverse. As these rifts widened, they eventually dropped below sea level, allowing fingers of the vast Panthalastic Ocean, the global ocean surrounding Pangea, to creep inward. Imagine the gradual inundation of low-lying areas, turning what were once pathways into shallow, brackish seaways. These nascent seas were the first truly significant barriers to overland dispersal. For terrestrial species, a narrow seaway, even a shallow one, might as well have been an ocean. Animals that relied on walking or climbing found their routes cut off. Plants, whose seeds might travel by wind or animal, found their dispersal ranges dramatically reduced. Even seemingly small bodies of water could act as incredibly effective filters, allowing some organisms to cross, perhaps by rafting on debris or by flight, while completely isolating others. This isolation was the crucial catalyst for one of the most profound evolutionary processes: divergent evolution. When a population is split into two or more groups that can no longer interbreed, they embark on independent evolutionary journeys. The absence of gene flow, the exchange of genetic material between populations, means that any new mutations that arise in one isolated group will not spread to the other. More importantly, the two isolated populations will likely experience different selective pressures. As continents drifted apart, they moved into different climatic zones. One landmass might move towards the equator, becoming hotter and wetter, while another might drift towards a pole, experiencing colder, drier conditions. The types of vegetation, the availability of food resources, the the presence of predators, and even the prevalence of diseases would all vary between these newly separated land masses. Consider the impact on plant life. A vast Pangea might have supported widespread, generalized plant communities adapted to a broad continental climate, but as continents separated, new ecological niches opened up. Different rainfall patterns, temperature regimes, and soil types on the newly isolated landmasses would favor different adaptations. For example, the rise of the angiosperms, or flowering plants, which began their diversification around this time, was profoundly influenced by the breakup of Pangea. As landmasses fragmented, new opportunities for specialized pollination strategies and seed dispersal mechanisms arose. Plants could evolve to thrive in more localized and diverse environments, leading to an explosion of new species. Imagine a type of fern that once covered vast swathes of Pangea. As its habitat was split by a widening sea, the populations on each side might slowly diverge. On one continent, increased aridity might favor ferns with deeper root systems or more efficient water retention. On another, abundant rainfall might lead to adaptations for rapid growth or specialized spore dispersal in humid conditions. Over millions of years, these differences would accumulate, eventually leading to distinct species that, even if brought back together, could no longer interbreed. The animal kingdom experienced an even more dramatic reshaping. Take, for instance, the evolution of mammals. During the time of Pangea, early mammals were generally small, nocturnal creatures, largely overshadowed by the dominant dinosaurs. However, as the supercontinent began to fragment, the mammalian lineage began to diverge. One of the most well-known examples is the split between placental mammals and marsupials. While the precise timing and geographical origins are still debated, the Pangean breakup played a significant role in their separate evolutionary trajectories. Marsupials, which give birth to relatively undeveloped young that complete their development in a pouch, came to dominate the southern continents of Gondwana, particularly Australia and South America, while placental mammals, whose young develop more fully within the mother's womb, became the dominant mammalian group in Laurasia, North America, Europe, and Asia. This geographical separation, enforced by the growing oceans, meant that these two groups of mammals evolved largely independently for tens of millions of years, resulting in the incredible diversity of mammalian forms we see today. Dinosaurs, the reigning titans of the Mesozoic era, also felt the profound effects of Pangea's fragmentation. During the Triassic and early Jurassic, many dinosaur families were relatively cosmopolitan, with similar forms found across what are now widely separated continents. However, as the rifting intensified and the nascent oceans expanded, dinosaur lineages became increasingly geographically restricted. For example, the long-necked sauropods and the armored stegosaurs, while originating earlier, diversified into distinct forms on different continents. The massive titanosaurs, a group of sauropods, became particularly dominant in the southern continents of Gondwana, evolving into an astonishing array of sizes and forms, largely isolated from the theropod and ornithischian radiations occurring in the north. The geographic isolation meant that unique evolutionary experiments could play out on different land masses, leading to the development of continent-specific faunas. Imagine the massive, long-necked plant eaters evolving different defensive strategies or feeding adaptations in response to unique plant communities and predators on their isolated continental islands. Beyond the large, charismatic megafauna, the breakup also influenced the evolution of smaller creatures. Insects, amphibians, and even freshwater fish saw their populations separated and subjected to different selective pressures. River systems that once flowed across vast stretches of Pangea were broken apart as new land masses moved away. This led to the isolation of freshwater fish populations, allowing them to diverge into new species, adapted to the specific conditions of their new, smaller, and more localized river basins. Amphibians, with their reliance on moist environments, would have been particularly vulnerable to the increasing aridity in some interior regions, and the new marine barriers. Their dispersal was limited, leading to distinct amphibian faunas evolving on different continents. The shifts in plant and animal life were inextricably linked to profound changes in global climate. As continents drifted, they altered ocean currents and atmospheric circulation patterns. The vast Panthalassic Ocean, once a relatively simple, open expanse, became increasingly segmented by the emerging continents. New ocean basins, like the nascent Atlantic and Indian Oceans, began to form, influencing the flow of warm and cold water around the globe. This led to more complex and varied climatic zones. Some regions became more humid, fostering lush rainforests, while others became drier, leading to the expansion of deserts. The increased seasonality in many areas, particularly as continents moved out of the super-equatorial Pangean belt, also drove evolutionary adaptation. Organisms had to develop strategies to cope with distinct wet and dry seasons or hot and cold periods, further pushing diversification. The very air animals breathed and the water plants absorbed changed as these tectonic processes continued, releasing greenhouse gases from volcanism, and later as oceans deepened, drawing down carbon dioxide. Ultimately, the breakup of Pangea, far from being a destructive event, was a colossal engine of biodiversity. The creation of multiple, geographically isolated land masses provided a myriad of new habitats and ecological niches. Each continent became a grand-scale evolutionary laboratory, allowing different lineages to experiment with new forms, new adaptations, and new ways of life without the constant genetic mixing that would have occurred on a single, vast landmass. While some species undoubtedly went extinct as their habitats changed or their populations became too small, the overall trend over millions of years was a dramatic increase in the total number of species on Earth. It was an era of unprecedented biological innovation, driven by the relentless, slow-motion dance of the Earth's tectonic plates, a dance that continues to this very day, shaping the distribution of life and the very nature of our planet. The legacy of Pangea's breakup is etched not only in the continental outlines on our maps, but also in the incredible tapestry of life that inhabits them. The story of Pangea's breakup is one of immense geological forces, unfolding over timescales so vast they are almost beyond human comprehension. While the rifting began in the Triassic period, the true dramatic separation of the supercontinent into its two major components, Laurasia to the north and Gondwana to the south, was a defining feature of the Jurassic period, a span of time roughly stretching from 201 million years ago to 145 million years ago. This era, famously known as the Age of Dinosaurs, was equally an age of continental transformation, where nascent oceans began to cleave ancient land masses, forever altering the Earth's geography, and, by extension, its climate and the very course of life. This was the era of the Jurassic Drift, a slow but relentless continental ballet that initiated the formation of the mighty Atlantic and Indian Oceans as we know them today. At the dawn of the Jurassic, Pangea, though immense, was already showing signs of strain. Cracks had begun to appear, particularly in the central part of the supercontinent, indicating where the future oceans would soon emerge. The driving force behind this monumental rifting was the deep-seated convection currents within the Earth's mantle. Imagine the Earth's interior as a slow-boiling pot of incredibly viscous rock. Hotter, less dense material rises, while cooler, denser material sinks. Where these plumes of superheated rock rise towards the surface, they can exert tremendous upward pressure on the overlying continental crust, causing it to stretch, thin, and ultimately fracture. These fractures propagate as massive rift valleys, enormous depressions where the land slowly pulls apart, often accompanied by prodigious volcanic activity as magma finds pathways to the surface. The landscape would have been scarred by vast basaltic lava flows, creating immense plateaus of dark, solidified rock and releasing enormous quantities of gases into the atmosphere, undoubtedly influencing the climate of the time. The very first major act of the Jurassic Drift was the separation of Laurasia from Gondwana. This monumental split began in what is now the Central Atlantic region. Initially, this was not a vast ocean, but a series of elongated, deep rift basins. As the North American plate began to pull away from the African and South American plates, these rifts deepened and widened. Seawater from the Panthalastic Ocean, the immense global ocean that surrounded Pangea, began to seep into these newly formed depressions. At first, these were likely narrow, shallow seaways, possibly experiencing restricted circulation and leading to the deposition of thick layers of evaporates, salt and gypsum, as the seawater evaporated in the hot, arid Jurassic climate. Over millions of years, as the rifting continued, these seaways expanded, becoming the nascent Central Atlantic Ocean. The evidence for this early split is abundant. Geological formations and fossil assemblages on the eastern coast of North America remarkably mirror those found on the western coast of Africa, a striking testament to their shared past and subsequent separation. Furthermore, the discovery of symmetrical magnetic stripes on the seafloor, mirroring either side of the mid-Atlantic ridge, provides irrefutable proof of continuous seafloor spreading, where new oceanic crust is generated as the plates move apart. While the Central Atlantic was slowly opening, the separation of Pangea was not a uniform process. The southern supercontinent of Gondwana also began its own complex and multi-stage fragmentation. This was arguably an even more dramatic and intricate process than the Laurasian split, involving multiple continental blocks tearing away from each other in a sequence of events that would eventually shape the geography of the southern hemisphere and initiate the Indian Ocean. One of the earliest and most significant events within Gondwana was the initial separation of Africa from South America. This slow, zipper-like process began in the south, in the region that would become the South Atlantic. As the rift propagated northward, the narrow seaway widened, gradually forming the broad expanse of the South Atlantic Ocean over tens of millions of years. Again, the matching geological structures, ancient fault lines, and fossil distributions across the South American and African continents provide compelling evidence of their ancient connection. The mid-ocean ridge in the South Atlantic, an underwater mountain range where new crust is continuously formed, is a direct result of this ongoing separation, growing wider by centimeters each year. Simultaneously, another crucial part of Gondwana was beginning its epic journey. The Indian subcontinent, along with Madagascar and the Seychelles microcontinent, began to detach from the larger Afro-Antarctic landmass. This was the birth of the Indian Ocean. This rifting was complex, creating a multi-branched system of spreading ridges. India, in particular, embarked on a remarkable northward trajectory. Its journey, which would continue for over 100 million years, was one of the fastest continental drifts known in geological history, culminating in its spectacular collision with Asia in the Cenozoic era, giving rise to the mighty Himalayan mountain range. Madagascar, a large island off the southeastern coast of Africa, also separated relatively early from the Indian bloc, becoming an isolated evolutionary laboratory that now hosts a unique array of flora and fauna found nowhere else on Earth. Australia and Antarctica, though part of Gondwana, remained connected for a significantly longer period, only truly separating much later in the Cenozoic. Their initial rifting and the formation of the Southern Ocean began during the late Jurassic and early Cretaceous, laying the groundwork for their eventual individual journeys. The formation of these early oceans had profound consequences for the Earth's climate and its ecosystems. The expansion of mid-ocean ridges, where new crust is generated, effectively displaced vast amounts of seawater, leading to higher global sea levels throughout much of the Jurassic and Cretaceous periods. This meant that large areas of continental interiors, previously exposed, were inundated by shallow epicontinental seas. These warm, shallow seas were teeming with life and provided vast habitats for marine organisms, contributing to an explosion of biodiversity in the oceans. The new oceanic gateways also fundamentally altered global ocean circulation patterns. Before the full breakup, the Paleozoic Ocean dominated, with relatively simple current systems. As the Atlantic and Indian Oceans began to form, they created new channels for ocean currents, influencing the distribution of heat around the planet. Warmer waters could flow into higher latitudes, while cooler waters could be channeled towards the equator, leading to a more complex and diversified global climate. This, in turn, directly influenced the distribution and evolution of terrestrial and marine life. The volcanic activity associated with seafloor spreading was prodigious. Along the mid-ocean ridges, countless eruptions continuously spewed lava, contributing to the growth of the oceanic crust. This volcanism wasn't confined to the ridges. Massive flood basalt events, like the Karoo-Ferrar Large Igneous Province, which spanned parts of southern Africa, Antarctica, and Tasmania, were tied to the early stages of Gondwana's breakup. These colossal eruptions released immense volumes of greenhouse gases, like carbon dioxide, into the atmosphere. While the exact impact is complex and debated, this atmospheric injection of greenhouse gases would have contributed to the generally warmer global temperatures characteristic of the Jurassic and Cretaceous periods. This warmer climate, combined with higher sea levels, created a world with much less extreme temperature variations between the poles and the equator than we see today. The Jurassic drift was not just a geological phenomenon, it was a biological revolution. The newly formed oceans acted as formidable barriers, isolating populations of terrestrial animals and plants. This isolation was the engine of divergent evolution, leading to the emergence of distinct faunas and floras on different continents. Dinosaurs, mammals, birds, and plants all diversified into unique forms as they adapted to the distinct environments created by their separated land masses. The oceans themselves, once a single immense body, became segmented, creating new marine provinces and allowing for the diversification of marine life, from ammonites to marine reptiles and early fish. The deep ocean basins, with their unique chemistry and physical properties, also became new habitats for the evolution of specialized deep-sea organisms. The story of the Jurassic drift is a testament to the dynamic nature of our planet. It wasn't a sudden, violent tearing apart, but a gradual, persistent process, driven by forces deep within the Earth. Over millions of years, a single supercontinent was transformed into the fragmented, diverse world of continents and oceans we recognize today. The echoes of this ancient breakup are still evident in the distribution of mountain ranges, the patterns of ocean currents, and, most profoundly, in the incredible biodiversity that graces each of our continents. The ongoing scientific endeavor to understand these ancient events, using tools like paleomagnetism to reconstruct continental positions and radiometric dating to pinpoint timings, continues to unravel the intricate details of this epical transformation, allowing us to glimpse a world vastly different from our own, shaped by the majestic power of the Earth's tectonic engine. Imagine a world where all the land on Earth was squished together, a colossal supercontinent stretching from pole to pole, surrounded by a single, immense ocean. This was Pangea, a geological titan that dominated our planet for hundreds of millions of years. But even the greatest giants eventually fall, and Pangea was no exception. Its slow, majestic fragmentation over the Mesozoic era, the very age of the dinosaurs, wasn't just a geographical event. It was a profound, evolutionary catalyst, shaping the lives, diversification, and ultimate distribution of these magnificent creatures. The shifting of continents wasn't just a backdrop to dinosaur history, it was an active participant, guiding their evolution down myriad, often divergent paths, leading to the astonishing regional differences we see in the fossil record today. In the early days of the Mesozoic, during the Triassic period, Pangea was largely intact. Picture a landmass so vast that it would have taken months, perhaps even years, to traverse on foot. This supercontinent was like a grand stage, allowing relatively free movement for early dinosaur forms and their ancestors. Without major oceanic barriers to impede their progress, animals could spread across vast distances. This explains why we find similar or closely related, Triassic dinosaur fossils on continents that are now separated by thousands of miles of ocean. For instance, the early sauropodomorphs, those impressive long-necked herbivores, or the early theropods, the two-legged carnivores, often show a striking family resemblance across what would later become vastly separated landmasses. It was a time of evolutionary experimentation, where the blueprints for future dinosaur dominance were being laid down in a relatively unified world. The climate across Pangea was likely quite seasonal, with vast arid interiors and monsoonal fringes, but the land bridges were open, fostering a more homogeneous, if not entirely uniform, global fauna. The very first true dinosaurs, emerging from their Archosaurian predecessors, could, in theory, walk from what would become North America to what would eventually be South Africa, an incredible journey that speaks to the interconnectedness of the world at that time. This initial unity meant that many basic dinosaur body plans and lineages were established across a wide geographical range before the world began to tear itself apart. As the Triassic gave way to the Jurassic, the first major fissures began to appear in Pangea's mighty crust. The forces of plate tectonics, driven by convection currents deep within the Earth's mantle, were slowly, inexorably pulling the supercontinent apart. One of the most significant events was the initial rifting that would eventually form the Central Atlantic Ocean. Imagine deep, volcanic valleys forming, slowly widening and filling with water. At first, these might have been narrow, shallow seaways, perhaps more akin to large lakes or gulfs. But even these nascent marine barriers, though not yet full-fledged oceans, were enough to start restricting the movement of terrestrial animals. Populations on either side of these rifts, once able to interbreed freely, now found themselves increasingly isolated. This geographical separation, often referred to as allopatric speciation, is a fundamental driver of evolution. Over many generations, genetic differences would accumulate between the separated populations, leading to the formation of new species. It was like a slow-motion continental divorce, with each partner taking a unique evolutionary trajectory. The Jurassic period truly saw the world begin to fracture, and with it, dinosaur evolution entered an era of magnificent diversification and provincialism. Pangea split into two main supercontinents: Laurasia in the north, comprising what would become North America, Europe, and much of Asia, and Gondwana in the south, encompassing South America, Africa, India, Antarctica, and Australia. The North Atlantic continued to widen, and the South Atlantic began to open up, slowly pushing South America away from Africa. These ever-expanding oceans became formidable barriers, making it impossible for terrestrial dinosaurs to cross. In Laurasia, particularly in what is now North America and Europe, a distinct assemblage of dinosaurs began to flourish. Think of the Morrison Formation in the western United States, a paleontological treasure trove from the late Jurassic. Here, we unearth the magnificent sauropods like Brontosaurus, Diplodocus, and Camarasaurus, their long necks reaching high into the conifer trees alongside the formidable theropods such as Allosaurus, the undisputed apex predator of its time and place, and the iconic armored dinosaur Stegosaurus with its distinctive plates and thagomizer tail. Similar, though not identical, faunas are found in Europe, suggesting a shared ancestry and perhaps intermittent land connections in the earlier parts of the Jurassic before complete separation. The environment in these regions, influenced by the continental configuration, was often characterized by vast floodplains, river systems, and extensive forests supporting a rich herbivore base. The pressures of coevolution, competition, and the unique environmental conditions of a land mass slowly pulling away from its southern brethren led to the unique characteristics of these Jurassic giants. Meanwhile, in the southern hemisphere, Gondwana was undergoing its own dramatic breakup. While still largely connected for much of the Jurassic, the early rifting began to establish distinct patterns. Dinosaurs here followed different evolutionary paths. For instance, while large sauropods were abundant in both hemispheres, the specific lineages often differed. In Gondwana, we see the rise of groups like the Rebbachisauridae, a group of sauropods with distinctive, often lower-slung skulls and unique teeth adapted for low brows, contrasting with the more high-browed sauropods of Laurasia. The predatory landscape also developed differently. While Allosaurus reigned in the north, the Abelisaurids, a group of theropods characterized by their often short, deep skulls, reduced arms, and powerful hind limbs, began their rise to dominance in the south. Though not yet the undisputed titans they would become in the Cretaceous, their Jurassic predecessors were already carving out their niches in Gondwanan ecosystems. The long-term isolation of these two supercontinents meant that dinosaurs on either side would evolve in parallel, sometimes leading to convergent evolution, where similar ecological roles were filled by different, unrelated species, but more often leading to distinct, recognizable faunas. The Cretaceous period, which spanned roughly 80 million years, was the age of extreme continental fragmentation and the pinnacle of dinosaur provincialism. The Atlantic Ocean continued to widen dramatically, finally separating South America from Africa, creating a vast marine barrier. India began its rapid journey northwards, isolating itself from Madagascar and other Gondwanan fragments. Australia and Antarctica, still connected for a significant part of the period, also began their slow drift south, eventually pulling apart. This intense period of continental drift transformed the world into a mosaic of island continents, each acting as a unique evolutionary laboratory. Nowhere was this more evident than in North America. The widening Atlantic and rising global sea levels during the Cretaceous led to the formation of the vast western interior seaway, a shallow epicontinental sea that sliced the continent clean in half. For millions of years, this seaway divided North America into two distinct landmasses: Laramidia to the west, a long, narrow island continent stretching from what is now Alaska down to Mexico, and Appalachia to the east, a broader but less explored landmass. This geographical division created unparalleled opportunities for diversification. On Laramidia, we see an astonishing array of dinosaurs, many of which were seemingly paired species or genera. For example, multiple distinct species of ceratopsians, the horned dinosaurs like Triceratops and Styracosaurus, evolved in relatively quick succession, each with unique horn arrangements and frills often found in specific geographical areas along the narrow landmass. Similarly, different species of tyrannosaurids and hadrosaurs, the duck-billed dinosaurs, flourished on Laramidia, exhibiting high levels of endemism. The constant geographical shifts, combined with varying local environments and resource availability along this elongated continent, drove intense speciation. Imagine migrating herds of hadrosaurs or packs of tyrannosaurs traversing this long, narrow strip of land, with distinct populations evolving in different segments of the seaway-divided continent. Appalachia, while less well known due to fewer fossil exposures, also harbored its own unique dinosaur fauna, reinforcing the idea that even within a single landmass, the presence of a major seaway could lead to profound evolutionary divergence. In South America, the continued isolation of the landmass after its separation from Africa led to a unique and impressive dinosaur fauna dominated by titanosaurs, a diverse group of sauropods that became the largest land animals to ever walk the earth, and the Abelisaurids, which solidified their position as the top predators. While tyrannosaurids dominated the north, Giganotosaurus and Carnotaurus were the undisputed kings of Cretaceous South America. Giganotosaurus, a carcharodontosaurid, rivaled Tyrannosaurus rex in size, demonstrating that different evolutionary pressures in isolated environments could lead to similarly enormous predatory forms. Carnotaurus, with its distinctive horns and incredibly small arms, was a specialized abelisaurid found exclusively in South America, a testament to the continent's long period of isolation. The fossil record from Patagonia, in particular, has revealed an astonishing array of these unique Gondwanan dinosaurs, painting a picture of an ecosystem quite distinct from those found in Laurasia. Africa, another former piece of Gondwana, also developed its own distinct dinosaur communities. Famous discoveries like Spinosaurus, a massive, fish-eating theropod with a distinctive sail on its back, and Carcharodontosaurus, another enormous Carcharodontosaurid that competed with Spinosaurus for dominance, highlight the unique evolutionary paths taken on this isolated continent. The African dinosaur fauna from the Cretaceous is particularly fascinating because it suggests a complex interplay of terrestrial and aquatic ecosystems, leading to highly specialized predators like Spinosaurus. Asia, connected to Laurasia, shared some faunal similarities with North America, but also developed its own, highly distinctive dinosaur groups. The Gobi Desert, spanning Mongolia and China, has yielded an incredible diversity of feathered dinosaurs, oviraptorosaurs, deinonychosaurs, and unique tyrannosauroids. While North America had T-Rex, Asia had its own formidable tyrannosaurids like Tarbosaurus, a close relative but distinct species. The sheer variety of small, feathered dinosaurs, many of which are crucial for understanding the bird-dinosaur transition, points to unique ecological niches and evolutionary pressures in this vast landmass. The climatic conditions, perhaps more varied and less uniformly warm than some other regions, may have also contributed to this unique diversification. Further south, the long isolated landmasses of India and Madagascar, which had split from Africa and drifted northwards, became veritable island continents. The dinosaurs found on these landmasses are often strikingly endemic, meaning they are found nowhere else on Earth. For example, Madagascar has yielded the impressive abelisaurid Majongasaurus, with its distinctive short, stout skull and cannibalistic tendencies, along with unique sauropods. The faunas of India and Madagascar offer compelling evidence for the effects of long-term geographical isolation on evolution, where unique species develop in the absence of gene flow from outside populations. They are living laboratories from the distant past, showcasing the power of continental drift to sculpt biodiversity. Even Australia and Antarctica, still partially connected and located closer to the poles for much of the Cretaceous, harbored their own unique dinosaur populations. Fossils from Australia reveal unique ornithopods and theropods adapted to environments that would have experienced seasonal darkness and cooler temperatures, a stark contrast to the warmer, more temperate or tropical regions where most other dinosaurs thrived. Evidence of polar dinosaurs like the small ornithopod Leiaelinosaura from Victoria, Australia, suggests that some dinosaurs were remarkably adaptable, able to endure conditions that would be challenging for many modern-day reptiles. The continued drift and eventual separation of Australia from Antarctica would lead to further distinct evolutionary trajectories, resulting in the highly unique marsupial and monotrim faunas we see in Australia today. The mechanisms by which continental drift influenced dinosaur evolution are multifaceted. The most obvious is allopatric speciation. As continents separated, populations of dinosaurs were physically isolated from one another. Over immense spans of time, these separated groups accumulated different genetic mutations, experienced different selective pressures from their unique local environments, and eventually evolved into distinct species that could no longer interbreed. This was the primary engine driving the provincialism we observe. Beyond simple isolation, adaptive radiation also played a crucial role. The fragmentation of Pangea created new coastal environments, new inland basins, new mountain ranges, formed as continents collided or rifted, and varied climatic zones. These diverse environments provided a wealth of new ecological niches that different dinosaur groups could exploit, leading to rapid bursts of diversification. For instance, the formation of vast inland seaways created extensive coastlines and brackish water environments that supported new types of aquatic and semi-aquatic dinosaurs. Climate itself was profoundly influenced by continental positions. The breakup of Pangea altered global ocean currents and atmospheric circulation patterns, leading to a more varied global climate with different biomes supporting specialized dinosaur faunas. Some landmasses became more arid, others more humid, influencing the type of vegetation available and thus the type of herbivores that could thrive, and in turn, the predators that preyed upon them. The fossil record, painstakingly pieced together by paleontologists over centuries, provides the undeniable evidence for this grand narrative. The distribution of dinosaur fossils, the phylogenetic relationships inferred from their anatomy, and the radiometric dating of the rocks in which they are found all point to a world that was constantly in motion, shaping and reshaping the lives of its most iconic inhabitants. From the widespread early Triassic forms to the highly endemic species of the late Cretaceous, the journey of dinosaur evolution is inextricably linked to the monumental ballet of continental drift. In essence, the shifting Earth was the ultimate stage manager, dictating the scenes, influencing the actors, and ultimately shaping the incredible diversity of the dinosaur world, leaving behind a geological and paleontological legacy that continues to astound and inform us about the dynamic interplay between deep-time geological processes and the grand tapestry of life. As the mighty supercontinent Pangea began its slow, inexorable breakup, it wasn't just land masses that were being rearranged on the grand stage of Earth. Accompanying this monumental continental drift was an equally dramatic transformation of the global ocean system. New oceans began to form, existing ones expanded or shrank, and coastlines were entirely redefined, creating a world dramatically different from the one that had existed before. This wasn't merely a passive expansion of water. It was a dynamic process driven by the very forces that tore Pangea apart, leading to the creation of vast, shallow epicontinental seas and the explosion of new marine habitats that profoundly influenced the evolution of life beneath the waves. The genesis of new oceans began subtly in the Triassic period, the dawn of the Mesozoic era. The initial signs of Pangea's demise were not roaring seas, but rather deep, elongated rift valleys slicing through the supercontinent's interior. These were the embryonic stages of future ocean basins. Driven by upwelling magma from the Earth's mantle, the continental crust began to stretch and thin, much like taffy being pulled apart. As the crust thinned, it fractured, allowing volcanic activity to begin along these linear cracks. Lava poured out, creating new crust, and as the rifting continued, the land on either side began to subside. Eventually, these low-lying rift valleys became deep enough to be inundated by water from the surrounding Paleozoic Ocean, the vast global ocean that surrounded Pangea. This is how the Central Atlantic Ocean began its slow, majestic birth, starting as a series of long, narrow gulfs and embayments, similar in some ways to the modern Red Sea or the Gulf of California, but on a much grander scale. These early, nascent oceans were often restricted, leading to the deposition of evaporites, like salt and gypsum, as the shallow water evaporated in the arid climate of the time. By the Jurassic period, the pace of ocean spreading accelerated dramatically. The Central Atlantic continued to widen, pushing North America and Eurasia apart from Gondwana. But even more significantly, the South Atlantic began to open, slowly prying South America away from Africa. This process, known as seafloor spreading, involved new oceanic crust being continuously generated at mid-ocean ridges, where molten rock erupted from the mantle, solidified, and then was pushed outwards, effectively acting like a conveyor belt. As new ocean floor was created, the continents on either side were moved further and further apart. The Pacific Ocean, or rather the remnants of the ancient Paleozoic Ocean, also underwent changes, with new subduction zones forming around its perimeter, consuming old oceanic crust. However, the most profound changes for life on Earth came from the new oceans forming within the footprint of the fragmented Pangea. These widening oceans weren't just vast bodies of water. They fundamentally altered global climate, ocean circulation, and perhaps most importantly for marine life, the very nature of coastlines. The consequences of this ocean expansion on coastlines were immense and far-reaching. As continents pulled apart, they created extensive passive continental margins. Unlike active margins where tectonic plates collide or slide past each other, passive margins are characterized by stable, broad continental shelves that gently slope into deeper ocean basins. These broad shelves, accumulating vast amounts of sediment eroded from the land masses, became incredibly fertile grounds for marine life. They provided stable, well-lit environments, perfect for the development of diverse ecosystems. The sheer increase in the amount of shallow shelf area globally was a boon for marine biodiversity. Moreover, the formation of new mid-ocean ridges, which are essentially underwater mountain ranges, displaced vast volumes of water. This phenomenon contributed significantly to a global rise in sea levels. Imagine taking a bath and putting a large object into the tub. The water level rises. Similarly, the newly formed, buoyant, and therefore elevated mid-ocean ridges caused the global sea level to rise considerably, flooding low-lying continental areas and creating entirely new coastal morphologies, including bays, gulfs, and straits where none had existed before. One of the most defining geological features of the Mesozoic era, directly linked to the rise of the oceans and the resulting high sea levels, was the prevalence of shallow epicontinental seas, also known as Epiric seas. These were vast, relatively shallow bodies of salt water that periodically flooded large portions of the continental interiors. They weren't just small inlets or gulfs. They were immense inland seas that could cover millions of square kilometers. Their formation was largely due to the combination of rapid seafloor spreading, which raised global sea levels, and a generally warmer global climate during the Mesozoic, which meant there were no large polar ice caps to lock up significant amounts of water, further contributing to higher sea levels. The continents themselves were also relatively flat, with less major mountain building, making them susceptible to being inundated when sea levels rose. The most famous and extensively studied example of an epicontinental sea is the Western Interior Seaway that dominated North America during the late Cretaceous period. Picture a vast, shallow sea stretching for thousands of miles from what is now the Gulf of Mexico all the way north to the Arctic Ocean, effectively splitting North America into two large island continents, Laramidia to the west and Appalachia to the east. This seaway, at its deepest, perhaps a few hundred meters, was teeming with life. Its bottom was often anoxic, preserving incredible amounts of organic matter that would later form significant oil and gas deposits, but its surface waters and shallower margins were vibrant. The constant influx of fresh water from rivers draining the surrounding land masses would have created brackish water environments in some areas, adding to the ecological complexity. This seaway was not static. It fluctuated in depth and extent over millions of years, influenced by tectonic movements and global sea level changes, creating dynamic environments that shaped the evolution of terrestrial and marine life alike. Beyond the Western Interior Seaway, the Tethys Ocean, or more accurately, the Tethys Seaway, was another immense and critically important epicontinental sea that spanned across much of Eurasia and Africa during the Mesozoic. This vast, warm body of water was a global biodiversity hotspot, serving as a crucial marine pathway between the nascent Atlantic and the ancient Panthalassic, Pacific oceans. The Tethys was often characterized by shallow, sunlit waters, supporting extensive coral reefs and a rich diversity of marine invertebrates and vertebrates. As the continents continued to drift and Africa and India began their slow collision with Eurasia, the Tethys began to shrink, eventually giving rise to the Mediterranean, Black, Caspian, and Aral seas as its fragmented remnants. This epic saga of the Tethys profoundly shaped the geology and biology of southern Europe, the Middle East, and parts of Asia. Similarly, shallow seas covered significant portions of Europe during the Jurassic and Cretaceous, creating vast carbonate platforms that would later form the iconic White Cliffs of Dover and many other limestone deposits across the continent. These shallow European seas were home to a dazzling array of marine life, from marine reptiles to countless invertebrates. As Gondwana broke apart, temporary or more persistent epicontinental seas also formed across parts of South America, Africa, and Australia, creating new, localized marine habitats that further contributed to the overall increase in marine biodiversity. The rise of these new oceans, and especially the widespread epicontinental seas, created an unprecedented expansion of new marine habitats, fundamentally transforming the marine ecosystem. The most significant impact was the dramatic increase in shelf area, the shallow, sunlit zones where photosynthesis can occur and marine life thrives. These environments are the most productive and biodiverse parts of the ocean, and the Mesozoic saw their global extent vastly increase. This expansion of habitat led to an explosion in the diversity of marine life. The most charismatic inhabitants were undoubtedly the marine reptiles, which diversified spectacularly to fill every conceivable ecological niche. Ichthyosaurs, with their streamlined, dolphin-like bodies, were fast-swimming pursuit predators, evolving from Triassic beginnings to reach their peak diversity in the Jurassic before declining in the Cretaceous. Plesiosaurs, with their long necks and 4 paddle-like limbs, adopted a variety of forms, from the long-necked, small-headed fish-eaters to the short-necked, large-headed pliosaurs like Liopleurodon and Chronosaurus, which became apex predators, preying on other marine reptiles and large fish. And then, in the late Cretaceous, the mosasaurs emerged, dominating the seas as formidable, serpentine predators, rapidly evolving from their lizard ancestors to become the ocean's apex predators, with powerful jaws and sharp teeth, displacing the remaining ichthyosaurs and many plesiosaurs. Marine crocodiles, some with fully aquatic adaptations, also thrived in these warm, shallow waters. Beneath these magnificent reptiles, a vibrant invertebrate world flourished. Ammonites, the iconic coiled-shelled cephalopods related to modern squid and octopuses, reached an astonishing peak of diversity and abundance during the Mesozoic. Their rapidly evolving shell morphologies make them invaluable as index fossils for dating rock layers. They formed a crucial part of the marine food web, consumed by various marine reptiles and fish. Belemnites, another group of cephalopods resembling modern squid, but with an internal bullet-shaped shell, were also incredibly abundant. Perhaps one of the most significant ecological developments was the rise of rudists, a group of bizarrely shaped bivalves that became major reef builders in warm, shallow, Cretaceous seas, often outcompeting or coexisting with corals. Their unique, often conical or irregular shapes allowed them to form massive biostromes and bioherms, creating complex habitats for other marine organisms. On a microscopic level, the oceans were teeming with new forms of planktonic life. The diversification of calcareous plankton, particularly foraminifera and coccolithophores, was profound. These tiny organisms, forming chalk deposits, like the White Cliffs of Dover, from their calcium carbonate skeletons after they died, played a crucial role in the global carbon cycle and serve as invaluable indicators of past ocean conditions and climate. The diversification of bony fish, or teleosts, also accelerated dramatically, providing a new and abundant food source for larger predators. These vast, interconnected marine ecosystems supported complex and dynamic food webs, from the microscopic plankton at the base to the enormous marine reptiles at the apex. The increased habitat available, the warmer temperatures, and the nutrient-rich waters flowing from the land masses into the shallow seas all contributed to this explosion of life. Beyond biology, the rise of the oceans profoundly impacted global climate and ocean currents. The new ocean basins and seaways fundamentally reorganized the flow of water around the planet. Imagine the Tethys Seaway connecting the nascent Atlantic to the Panthalassic, acting like a giant warm water current, distributing heat around the equator. This new configuration of oceans and continents influenced atmospheric circulation patterns, leading to a more equable global climate throughout much of the Mesozoic, with less extreme temperature differences between the poles and the equator. This warmer climate, in turn, further contributed to higher sea levels by preventing the formation of large ice sheets. Furthermore, the vast expansion of marine life, particularly the calcareous plankton, played a critical role in the global carbon cycle, sequestering enormous amounts of carbon dioxide from the atmosphere into marine sediments, which eventually formed vast deposits of limestone and chalk. The geological evidence for the rise of these oceans and epicontinental seas is abundant and compelling. The immense thicknesses of sedimentary rocks, particularly limestone, chalk, sandstone, and shale, found across vast swathes of continental interiors, speak volumes about the repeated inundation by shallow seas. These deposits often contain an incredibly rich fossil record of the marine life that inhabited these environments, providing direct evidence of the ecosystems that flourished there. The seismic profiles showing the deep, layered sediments of continental margins and the magnetic stripes on the ocean floor confirming seafloor spreading all contribute to this understanding. In conclusion, the breakup of Pangea was not solely about land masses drifting apart. It was equally about the dramatic birth and expansion of new ocean basins and the widespread development of shallow epicontinental seas. This geological transformation reshaped the very face of the Earth, creating a world with vastly expanded shallow marine habitats. These new environments, characterized by warm, sunlit waters, provided unprecedented opportunities for marine life to diversify, leading to the spectacular evolution of marine reptiles, ammonites, and a myriad of other organisms that define the Mesozoic marine realm. The dynamic interplay between plate tectonics, ocean formation, and global climate created a unique period in Earth's history, a time when the seas expanded to cover much of the continents, fostering an astonishing array of life and leaving behind a geological legacy that continues to inform our understanding of the deep past and the profound interconnectedness of Earth's systems.